With the first session. Our first talk is Data Structure Abstraction and Incorrectness Separation Logic by Andreas. So take it away.
Yep. It's not showing again. Oh, no, yeah. Yeah, exactly. So I'm going to talk about data structure abstraction and incorrectness separation logic. And it might be good to know that this is a work in progress based on a mostly complete rock mechanization. And the plan is as follows. So I'll do a quick recap of what I mean by data structure abstraction in a familiar setting, so separation logic. And then we'll try to do basically the same thing in incorrectness separation logic and conclude that it doesn't work very well. And then there will be a suggestion how to make it work less bad. Yeah, okay, so let's start with the first item. So by data structure abstraction, I simply mean something like this. So in the pre, we have some predicate connecting up, well, in this example, it's lists. So connecting up heap lists with meta-logic lists. And then we have some meta-logic function here, cons over meta-logic lists. And then we want to connect the stuff that's happening at the program level to the meta-logic level. And this is exactly what this tuple is doing, right? So it's saying that the behavior of the heap list is contained in the behavior of the meta-logic list. So just standard this form. And why is this useful? Well, because we can use these specs later. So when we reason about client code, it could look something like this. So we start with an empty heap, and then we allocate the list, and then we get the empty meta-logic list, and then we can add something, and we just update the meta-logic list. So the point there being that we don't need to care about what is happening in the heap. We only manipulate our nice meta-logic list. So for example, if we would have some code like this afterwards, we would know which branch we would look into without having to look into the heap. We only need to care about the meta-logic level. Okay, so that's all fine in verification and separation logic. So what happens in bug finding? So basically, we want to do the same thing here. So we have the same program, and the aim is, well, we should do the same thing. But of course, with like behavioral containment flipped. So now we want all the specified behavior to be actual behavior. So let's throw away our approximate triples and replace them with unapproximate triples. So for this to work, we need, in some sense, separation logic-like specs in incorrectness separation logic. So, for example, for this step, we could do this in separation logic because we had this spec before. So to do the same same step, we need, well, essentially the same spec, but in ISL. And this indeed works because basically there's not a lot of abstraction going on here. We have a list in the heap, and we have a list at the meta-logic level. So sure, there is abstraction, but there's not a big gap between them. So incorrectness separation logic is not completely useless for abstraction. But if we if we increase the gap between the heap and the meta-logic level, then things will break. So let's do that. So let's replace our list with a set. So now we are instead exposing our heap list as a set. So now the gap is bigger. So all of this will be completely fine in verification and separation logic because we would just replace this list cons with this type of insertion into a list, and this will be fine. This is an over-approximate valid spec. But to do this reasoning in incorrectness separation logic, we need this spec. And unfortunately, this spec is not valid. And what is the reason for this? Well, the problem is basically that we have no control over where this new element is inserted into our set. So there are multiple models of this post condition, and we don't know where this V will end up. It can be in the beginning, in the middle, or end, and the actual implementation will add it in. For example, the beginning, the middle, or in the end, whatever, it doesn't matter because it will not reach all of these. So we have a triple where the full post is not reachable, so this is not valid. So what can we do about this? So you first need to figure out what went wrong. So if you look at the standard definition of the ISL triple, it looks something like this. And the problematic part is really this quantification here. So we have a very strong reachability property here. So we are saying that for all logical environments, theta, and stores and heaps of the post, they are reachable. Yes, here. Yeah, so we can execute to all the models from a model of the pre. So in some sense, this is a reachability guarantee at implementation level because all the heaps are reachable. But when we reason at the level of the abstraction of the spec, we don't really care about the heap. So this is, in some sense, too strong. So I have a suggestion here that if we can weaken this reachability guarantee in the following way, then we will get the specs that we want to be valid to actually be valid. So it would be nice if we could somehow partition the state space with respect to the abstraction of the spec, and then you see that each partition is instead reachable, in some sense saying that the heap is not as important as is encoded in ISL. So after 500 attempts of capturing this formally, this is my current suggestion. And this differs from ISL, or I have highlighted how this differs from ISL with these gray boxes. So specifically, we have relaxed the reachability guarantee of the heap. So instead of saying that all the models of our post is reachable, we have this new existential quantification here, saying that there is some other heap that is actually reachable. So we replace this actual model of the post with an existentially quantified heap. And what constraints do we put on this heap then? So it needs to be a model of the same post and with the same logical environment and store. And it also needs to be frame compatible in the sense that it's compatible with all the frames that are compatible with all the models of the post. So you can think of this as a frame compatible representative. And less formally, we can look at an example and see how this works out in practice. So if we go back to our set example, the partitions would look something like this. So this is the full state space, this full space of the post, or in this case, just the predicate. So the partitions here will be, for example, all the sets that start at address 1 and containing nothing, all the sets
Okay, so for our next talk, we have gradual exact logic, unifying Hoare logic and incorrectness logic via gradual verification by Konrad Zimmerman. So go ahead.
Yes, hello. Are my slides up? Okay, perfect. Yes, I'll be talking about gradual exact logic, unifying Hoare logic and incorrectness logic with gradual verification. So there's a bunch of stuff here to introduce, and we're going to sort of start at the end of the title with gradual verification and work backwards. So what is gradual verification? Gradual verification is a tool to enable incremental verification by combining static verification with runtime checking. And the goals here are to immediately check a partial specification. So without creating a full static proof, we can add runtime checks that will validate any missing proof obligations. And we want useful feedback during development. So verification errors need to indicate actual mismatches between the code and the specification, not simply a lack of proof like your SMT solver gave up. And finally, we want to statically guarantee that a completely specified program is correct, providing the same guarantees as traditional static verification tools. So what this looks like with partially specified code is that we hand it to an optimistic static verification algorithm. In the completely specified case, this is pretty much a traditional static verifier, but we're going to look at the interesting case here of partial specifications. So optimistic verification can make assumptions that are necessary to verify the code. And there's two possible outcomes here. Either it is partially verified, in which case there are going to be runtime checks that are added to the program in order to ensure soundness. On the other hand, we can give a verification error statically before the program is ever ran. And today I'm going to be looking at how this optimistic verification works, and in particular, when can we give a static verification error? Remember, we want to only find true problems with the code. So I'll run through a little example of how this optimistic verification works using this very short little example snippet of code where it assigns y to be 42 when x is even. So the programmer gives it a specification, a partial specification here with question mark and true. So pretty much no information other than this is a partial specification. In the post condition, we want to show that y equals 42. So we start using pretty much a traditional verification method where x is even in the true branch after assignment y is 42. We can weaken this to be the exact post condition that we want. On the other hand, we have a whole other branch to verify, and in this branch, x is not even. That does not give us any information about what y is. However, because this is a partial specification, we can optimistically assume that y is 42. Again, we weaken the post condition, and now we've verified that branch. Since we've verified both branches, we conclude our post condition. So an actual gradual verifier is going to take this partially specified program and the optimistic proof and generate a final program with the runtime checks. But go to Jenna's talk tomorrow to learn how that works. Today we're just going to be focused on the optimistic proof part. So on the other hand, incorrectness logic statically finds true bugs. So how is this related? Deductions here indicate a reachable post condition. And it can arbitrarily drop paths, which makes checking for bugs in a large program tractable. So we're going to run through a similar example with incorrectness logic, where we start with a true post condition in brackets to indicate incorrectness logic. And let's say the programmer gives us a specification of maybe a bug where y equals 42. And we proceed sort of similarly. I assume you're somewhat maybe familiar with incorrectness logic, so I'll sort of skim through this. In the true branch, x is even, y equals 42. We go to the false branch, x is not even. That's it. But we can, by the consequence rule, add that y equals 42. After that, we get a disjunction of these two things that we've proven about this conditional. And this is logically equivalent to just saying that y equals 42, assuming it's in some sort of like classical setting. So we've proven the same post condition. And the proof has resemblances, at least. especially in the step where we make assumptions. So this is sort of the motivation for our work. It looks like we're sort of doing the same thing. And moreover, in some implementations, like the Jillian verifier that does over and under approximate reasoning, the implementation actually very closely resembles the work on gradual C0. So this was sort of the motivation for the work, and we tried to develop a formal connection here where we can actually use incorrectness logic theory and/or implementations for gradual verification, or maybe at least for this optimistic verification step. So the answer is a qualified yes, that we can sort of apply this, but there are some caveats. So let's look at one. Gradual verification doesn't actually behave like incorrectness logic. We have weakening in gradual verification. For example, I can verify this weaker postcondition of y less than or equal to 42 under gradual verification, very similar as before. However, under incorrectness logic, this doesn't work. And this is because we can't weaken this y equals 42 whenever x is even. So what we've developed is a formal analysis of the relation between gradual verification and incorrectness logic. And in particular, we'll give a semantic definition of what this optimistic verification is. And then we'll develop gradual exact logic, which is a framework where we can compare under and over approximate logics using the language of gradual liftings. And finally, we can decompose optimistic verification into separate over and under approximating steps. So in order to define the semantics, I use a collecting semantics for programs where we take a set of input states and transform them to a set of output states. So in Hoare logic, the postcondition over approximates the set of final states. So in other words, for all states satisfying your precondition, after executing our program, we're going to reach the postcondition. However, our postcondition may contain unreachable states. On the other hand, incorrectness logic under approximates final states. All states satisfying the postcondition are reachable by executing the program. However, our precondition might contain states that do not end in our postcondition. So we have this comparison with over approximation on one side and under approximation on the other side. But where does gradual verification fit into the picture? So we formally define the semantics of gradual verification through what we call consistent liftings, which is an idea from gradual typing. So we have gradual formulas that can be either partial formulas with a question mark or complete formulas without a question mark. And then we have a concretization of gradual formulas. And for complete formulas, that's just a singleton set containing that formula. However, for partial formulas, that is the set of all stronger formulas that are satisfiable and imply the partial specification. This satisfiability constraint is very important for how we define things. And then we can lift an arbitrary predicate on formulas, for example, the validity of triples, to a predicate on gradual formulas. And we define this using an existential, where if there is some concretization of the gradual formula, then that satisfies x, then the gradual formula satisfies x tilde. We use tilde to indicate a gradual predicate or gradual formula. So now we define validity for gradually specified triples as a consistent lifting of Hoare logic. And in particular, we make the precondition be a gradual formula that can be complete or partial. In particular, for optimistic verification under partial specifications, we say that a triple holds if there is some stronger precondition that makes it a valid Hoare triple. Notably, this will be trivial if you pick P prime to be unsatisfiable, but because we require it to be satisfiable, there is actually, this is non-trivial. So intuitively, this question mark represents some additional missing assumptions that are necessary for verification, but for whatever reason are left out of the specification. So now semantically, gradual verification is an existential logic. Verification succeeds if there is some state in the precondition that ends in the postcondition. And this contains both the caveats of over and under approximation, where our postcondition may contain unreachable states and our precondition can contain states that do not end in the postcondition. So we have over-approximation and under-approximation, and gradual verification is this existential logic that is sort of this combination of both logics. So now we look at gradual exact logic, where we can compare over and under approximate logics. So first, we define this using a very restrictive exact logic. And Andreas talked about exact separation logic. This is maybe the first order version of that. So the triple holds if the postcondition is exactly the final states, which means that we're neither under-approximating nor over-approximating. And the initial motivation was to verify things so that you could use the specifications in over or under-approximate reasoning. However, we're going to take that in a different direction and define a gradual lifting of exact logic, which we call gradual exact logic. So the triple holds if there is some concretization of both the pre and the post condition where it is a valid exact logic triple. And we'll see that we can actually introduce over and under approximation using partial specifications. So we can actually characterize Hoare logic by making the post condition a partial specification. And intuitively, we basically force this to be an exact deduction by strengthening our post condition to be exactly the final states. On the other hand, incorrectness logic is also characterized by making the precondition imprecise or partial. So this represents exactly the states that are going to reach our post condition. And finally, we can characterize this optimistic verification as the combination of the two, where we make both sides partial. So now this is sort of just all a lead up to how can we use this to decompose optimistic verification into over and under approximating phases. So first, we can actually characterize optimistic verification just using incorrectness logic. In fact, using a consistent lifting of incorrectness logic. So you'll note first we've defined gradual verification in terms of over-approximating Hoare logics, but it turns out you can do the exact same thing with incorrectness logic, just making the post condition, in this case, partial, and you get the same thing for partial preconditions. So a corollary of this is that you can actually do optimistic verification just using incorrectness logic. All you have to do is find a strong enough post condition that implies the post condition that we want. So in other words, you can do optimistic verification just by over-approximating and then checking by under-approximating and then checking that you have a strong enough post condition. However, we can take this a step further. And first, in gradual exact logic, if you have a triple with both the pre and post condition partial, you can decompose this into two steps where you have a partial precondition in one deduction and a partial postcondition in the other. This is pretty much an expansion of definitions and applying the sequence rule. However, if we use our characterizations of the different logics, this actually decomposes optimistic verification into a set of deductions in incorrectness logic, under approximating, followed by some over approximating in traditional Hoare logic. So that concludes our analysis. We have a lot of future work. We have sort of only proven this for a very restrictive class of programs, but we want to extend this logic to cover existing gradual verification theory, like modular verification of functions and loops, and how do we handle state using something like separation logic. But also, we think we can maybe use incorrectness logic to develop the theory of gradual verification and extend it to things like concurrency, non-determinism, or non-termination. And finally, and maybe most practically, we want to just borrow from incorrectness logic to make better gradual verification tools. And in particular, maybe just take verifiers that do incorrectness logic and extend them to be a gradual verifier. So in summary, we've defined the semantics of optimistic verification. We've decomposed it into over and under approximating steps. And along the way, we've developed this gradual exact logic that lets us actually analyze the relation between the two. Thank you.
All right, great. So we have time for one quick question while the next presenter sets up.
So your gradual on both sides, right? Pre and post, it looks a little bit like bi-abduction. Have you
Yes,
had
yes.
you looked into the comparison between this and the
Yeah, yeah. So for the basically my answer would be that for the simple cases, it basically is by abduction. However, once you get to more complicated cases, for example, with loops, we can gradually verify things where no finite invariant captures what you need. So things like that where abduction sort of fails, you can't bi-abduce the right invariant, things like that, yeah.
Thanks.
Okay, let's thank Conrad one more time. Our next talk is on partial incorrectness logic by Lena Verst. So go for it. Go for it.
Okay. Oh. Is there nothing? I did just try it out and it worked. I also have an HDMI.
You have to turn the slide somewhere else. It's not working. You just need not.
We're going to rearrange the schedule a little bit. So the next talk is going to be by James Lee on total outcome logic. And hopefully the projection will work. Otherwise, maybe it's a problem with the system in the room.
And a quick disclaimer, I'm filling in for Anjan, so credits to her for the slides and everything. But yeah, I want to start with giving you an idea of what this is going to be about, partial incorrectness logic. And well, we've all heard of total correctness logic, right? A program is totally correct if all computation is started in some set of initial states, always terminates, and always does so in some set of safe states, the post condition, right? But proving termination is quite hard. So there's this more lenient notion called partial correctness, which does not require termination. But should the program terminate, it still has to do so in this set of safe final states. So we can get a proof of total correctness by proving partial correctness and termination. Okay, so then there is this, in many ways, dual notion incorrectness. And well, the claim is kind of, if it's so dual, we expect some kind of similar equation here, right? To split this total form of incorrectness into something like partial incorrectness and whatever. So this talk is going to be answering mostly two questions. First of all, what do we mean by partial incorrectness? And we'll see that this gap here can actually be filled by reachability. Okay, so I'm going to start with some formal basics. A Hoare triple is valid for total correctness, as I said before, if all computation started in this set of green states, the precondition, terminates in this post-condition C. And, well, divergence is not allowed, so this could not be a part of the precondition, but this top state here could be because it's also terminating in the post-condition. And then these three sets here actually form the largest set of states that we can fit in there. So this is the weakest condition that has to hold, and this is exactly what is captured by Dijkstra's weakest precondition transformer. And so for a given post-condition C and a program, this weakest precondition contains all states from which computation always terminates in the post-condition. And there is another notion of these transformers called the weakest liberal precondition transformer, which additionally includes states from which computation diverges. So this state here is now also included. And well, why am I telling you this? Well, we can characterize both total correctness using these weakest preconditions by requiring that the precondition is included in the weakest precondition with respect to the postcondition, and we can characterize partial correctness using this weakest liberal transformer. And as I said before, we can now prove total correctness by proving partial correctness and termination. And well, this is cool because, first of all, we get something like a separation of concerns. We split the termination proof, which is like there's a whole field of research on proving termination, so this could be helpful. And also, there is this property of weakest pre and strongest post. Weakest pre and weakest liberal pre, because the weakest pre is defined as a least fixed point. So to prove this equation here, we need a lower bound on a least fixed point, which is just computationally hard to prove. For weakest liberal preconditions, they are defined as a greatest fixed point. And to prove lower bounds on greatest fixed points, we can use a very nice lemma referred to as Park's lemma or Park induction. And this makes this proof of partial correctness a bit easier. So this is another reason why it might be helpful to split total correctness into partial correctness and termination. Yes, so and now what we are going to see is that we can actually do a very similar thing for total correctness and then partial incorrectness. I said correctness, I meant incorrectness, by using these strongest post transformers. So we'll see in a second what this is exactly, but we can define total incorrectness, so this is a standard incorrectness logic using the strongest post transformer, and then partial incorrectness as some liberal variant of this transformer. Okay, so now we'll see what this is exactly. So incorrectness logic, as you all probably know, was introduced as reverse Hoare logic before, and then later reinvented as incorrectness logic. And it means that all states in some postcondition C are reachable by the precondition. And what you can see here, well, this unreachable state is not allowed in the postcondition, but this state here would be allowed. And then these two states form the largest set again that would be allowed here. And this is exactly what is computed by the strongest postcondition transformer. So for a given set of initial states, this computes the largest, all final states that are reachable from this set of initial states. Okay, so far so good. This is quite well known, I assume. And now to get from weakest pre to weakest liberal pre, I said before that we allow diverging computations. And now we want to do like a dual thing to this. So a diverging computation is like a computation path that is leading to nowhere, right? So the dual thing for a final state would be something like a computation that is coming from nowhere, so no initial state can reach this final state. So the final state is unreachable. And this duality between unreachability and divergence was also discussed in other works, for example, by Ascari and others. And yeah, so to get from strongest post to strongest liberal post, we allow unreachability. And yeah, this was exactly captured by the strongest liberal postcondition transformer, which was introduced by Zhang and Kaminsky. And yeah, what this computes is the set of final states that are either unreachable or reachable by the precondition. So in other words, we say it's okay if a state is unreachable, but if it is reachable, then it must be so from the precondition. So this is very dual to this weakest liberal precondition idea. Okay, and then, as I said before, we can characterize total or like, standard incorrectness logic as an under-approximation of the strongest post, and get partial incorrectness by under-approximating this liberal variant. And what we also get is the same computational advantage as we had for the weakest pre-case, so to speak, because we have here an under-approximation of the least fixed point, which again is hard, and here we have an under-approximation of a greatest fixed point, which is easier. And also we get this separation of concerns idea that we can split this reachability proof from the incorrectness proof. So this might be interesting to look at if we are trying to prove total incorrectness. Okay, so why should we be interested in this partial incorrectness logic? Well, total incorrectness requires reachability of all final states included in this postcondition. And this is a very strong requirement, actually. This now goes in the direction of what we've just seen, actually. I have an example that is also very similar, also inspired by one of the beginning examples in this incorrectness logic paper. Because yeah, here's a program that increases y by 1 if x is even and otherwise multiplies y by 2. And if we're now looking at this triple here, y equals 10, program y equals 11, well, is this valid for incorrectness, or are these states reachable from these states? You'd maybe think yes, because we can choose this branch here, increase y by 1, and then we end up with y equals 11. But it's actually not valid for total incorrectness, because we require that all states where y equals 11 in the end are reachable from this precondition, which is not the case if x is odd. So for example, if x is 1 in the end, it must have been so in the beginning because the program doesn't change x. But then we end up in the second branch. And well, if we start with y equals 10, then in the end y will be 20 and not 11. So what we could do to fix this is we could make the postcondition more precise. So we could say, okay, this is not valid for total incorrectness, but this here is if we specify the postcondition as y equals 11 and x is even, then we guarantee that this first branch was taken. So this would be valid for total incorrectness, but this, in some cases, it just might be hard to specify it like this concretely, right? So what we propose is to look at partial incorrectness in this case, because it turns out that these counterexample states that we've seen before, they are not just unreachable from the precondition, y equals 10, but they are unreachable from any state, at least assuming integers, because if we start with an x that is odd, then we must end up in the second branch, so y must be even in the end. So states where y equals 11 and x is odd, they are just unreachable at all. So this is valid for partial incorrectness. Okay, and I want to mention a second idea where this might be helpful, which is very similar to the motivation of necessary preconditions. Because if we're looking at this triple B pre-true, so we're including all states in the postcondition, what this says, if we have some program, all executions must have originated in this precondition B, because we require that all final states are either completely unreachable or they are reachable from this precondition. So B can be thought of as like a necessary condition that has to hold for the program to do anything or to have anything meaningful. So for example, it's a bit of a toy example, but if you think of like a Schrödinger's cat situation, you have some kind of box that you could open or not, and you have a cat inside the box, and well, the cat could be alive depending on or not, depending on whether some poison was spilled or not. This is like the program graph representing the situation. And then you look at the triple open program true, which is valid for partial incorrectness. Then you know that in order to know anything about the cat in the end, the box must have been opened. So yeah, in order to make any observation, you have to open the box. Yeah, and proving this for total incorrectness is hard because you would require reachability of all final states, which is in many cases not a sensible assumption. Yeah, so to summarize, we've seen this duality between correctness and incorrectness. And we've seen that we can express total correctness as partial correctness and termination, and dually total incorrectness as partial incorrectness and reachability. And using this Park's lemma, we can prove both partial variants easier. And yeah, this can be useful when we want to relax these reachability conditions in the postcondition. And yeah, also to find preconditions that are responsible for some kind of outcome. And yeah, this is ongoing work. This is still a bit of an idea. So there's a lot of things to do. For example, the strongest liberal post-calculus that I mentioned was introduced actually as a quantitative transformer. So it'd be interesting to see what partial incorrectness means, what we can do with this in a quantitative setting. Then I've said that we can split this proof of reachability from proving incorrectness or total incorrectness. It would be cool to look at some methods how we can prove reachability, maybe using these strongest liberal post transformers. And a remark on the name partial incorrectness, because this kind of suggests that this is a bad or an unwanted property of the program, which is not necessarily the case, as it is also not the case for correctness logics that they prove necessarily good properties about programs. So this is also that I've been, the name is up for discussion, let's put it like that. Yes, thank you, that's about it.
Okay, since we got a little bit behind, we'll just take one quick question while the next speaker sets up.
So, nice talk. I really appreciate that you defined this new languages allow some Hoare triple. It doesn't allow in in-class logic, but now in your setting. But I think in some sense, in-class logic, you can treat it as a formalization of some prosecution. It's indeed try to prove the reachability. In some sense, in-class logic is a technique to prove the reachability, but you separate the reachability away.
That's a valid point. Yeah, sorry. I think. Yeah, in some cases it makes things harder. It's a bit. I know what you mean with this proving bugs motivation. This seems a bit silly to allow unreachability. Yes, but I think if you. Yes, this is something that we've been looking at. This is a problem. It's a valid question.
Yeah, okay, thank you.
Yeah.
Okay, let's thank Lena one more time. And for real this time, we now have James Lee presenting total outcome logic. Hopefully is the projection working? No, okay. So we'll see.
Okay, great. Okay, hi, I'm James. Today, this talk will be on total outcome logic, an extension of the theory of outcome logic, which adds additional support for reasoning on termination and non-termination. So, just to begin, why don't we start by considering what outcome logic is and its particular vision in the entire landscape of program logics in general. So, so the entire landscape of program logics consists of a range of specialized theories which are tailored. Which are tailored for particular modes of reasoning, as well as particular computational effects. So we have the archetypical Hoare logic and its correctness logics that were developed thereafter. We have probabilistic logics. We have the recent body of incorrectness logics, which shifts focus from analysis for verification onto bug finding. So what outcome logic seeks to do is it seeks to unify this landscape through a single theory under a single meta-theory. And this unification takes place across two main fronts. So outcome logics generalize over branching effects. So for example, they can be instantiated for programs that exhibit non-determinism, as well as those with randomization, for instance. And in addition, outcome logic captures both correctness and incorrectness properties, and this makes it particularly powerful in serving as a theory that can both perform verification and bug finding. But despite this, there are some limitations, in particular when it deals with the effect of termination and stool non-termination. So outcome logic is unsuitable for proofs of total correctness, as you might see in total Hoare logic, with the variant inference rule. It also struggles with proofs of the existence of non-terminating executions. And this is a direction of work that has seen much more attention in the incorrectness sphere with the development of a logic like Unter. So to paraphrase, we want to be able to ask, does my branching program surely terminate across all its branches? And is it possible that the program fails to terminate in one of its branches? So these cannot be answered in outcome logic. Instead, we propose a simple extension of this, of the theory of outcome logic, to provide support for proofs of these kinds. So, but before we actually delve into the framework, why don't we consider what would be an adequate semantics for modeling program behavior in our case? So a lot of this will be review of vanilla outcome logic. So one of the first promises we made as regards to outcome logics is that it can generalize over branching effects. So that means like programs that exhibit probabilistic branching. So take, for example, this very simple program of a fair coin flip. How would we go about representing the results of running this program? Well, we know that this program branches into two outcomes, each of which occur with a probability of 1/2. Or in other words, we can specify the result of running this as the set of its possible outcomes, along with labels, along with weights that are assigned to each of these outcomes. So in this case, these would be the probabilities. But if we carry this thought over to non-determinism, well, we can see that the most intuitive way to represent the result of running this program is to just provide the set of outcomes that are possible. And it turns out it's pretty easy to see that this is basically another instance of our weighting scheme, as discussed before, where, again, we have a set of outcomes, but now our labels or our weights are drawn from this trivial set of values of either true or false, where true indicates that a particular outcome is possible, and false indicates that it isn't. So we seem to have stumbled upon a common structure that we can use to construct our semantics on. So the fundamental idea is that we want to model program results as these maps from a state space to a set of weights labeling each outcome. And we will call these types of maps weighting functions. And to formalize weights more rigorously, it turns out that a very nice formalization is to just require that it's drawn from a semi-ring. And this affords us very nice algebraic properties upon which we can build the meta-theory. But in each of these examples, for instance, in the example of non-determinism, we can see that the weights are drawn from a Boolean semi-ring, where the labels are either true or false. In the case of probabilistic programs, we are obviously using a real-valued semi-ring on the 0 to 1 interval. And we find that with just a few slight restrictions on the weighting function themselves, weighting functions end up corresponding to probability distributions in the probabilistic model. So we have accounted for branching effects in our semantics, but now the other effect that we need to somehow encode is that of non-termination. And the simplest way of doing this is to simply encode non-termination as an explicit outcome in our weighting functions. So again, we will be using the weighting functions to weight each possible outcome. But now we expand the domain to also include this additional symbol which stands in for non-termination. So in our semantics, we can see that we can explicitly specify with what weight a program may diverge. Now, the combination of these two effects admits some difficulties, especially as we try to formalize the denotational semantics. I will omit the mathematical details, so this will be very expository. But intuitively, the problem with the semantics is that we have now opened our way up to modeling programs that we may not want to model whatsoever. So in this case, consider this program that non-deterministically sets x to any natural number. So here we see that this program can produce an infinite accountable number of branches in a single step of execution. But as it turns out, it's a classical result in denotational semantics that there is no Scott continuous semantics that captures both this effective non-termination as well as unbounded non-determinism, as we've seen in the previous program. So again, forgoing the mathematical details, perhaps a way of getting an intuition of this is to simply consider this program that consists of the non-deterministic assignment we had before, sequenced with a loop that decrements the value of x to 0. So it makes sense that for any one branch of execution of this program, the program will surely terminate. You choose any natural number to set to x, and the loop will terminate in a finite number of steps. And yet, the view that kind of pops up in the semantics is that if we instead look at this from the perspective of a machine that has to explore every branch of execution, we see that, well, there are an infinite number of branches to explore. And so from the top down, it seems that the entire program does not terminate. So there is this disconnect from viewing this program from the top down versus from the individual branches that it can spawn, a sort of discontinuity. So what this admits now is a pretty straightforward interpretation of programs as maps from an initial state to these weighting functions that we just introduced. So in the example of probabilities, you would take an initial state, run your program, and then I would feed you back a probability distribution. So this encoding of non-termination inner semantics now allows us to build artifacts in our actual our logic theory to begin to reason about non-termination and termination. So to actually take a look at the framework, our formulas are, again, these triples sandwiched by these outcome assertions. But what is particular about outcome logic is that these assertions no longer correspond to simple sets of states, as they would for usual program properties. Instead, they're lifted to hold on weighting functions. So for instance, if I had a probabilistic program, I would have to account for the branching effects by taking my assertions to be collections of probability distributions instead of just sets of states. And it's this lifting that affords us a lot of versatility with outcome logic. So just taking a look at our assertion language, we have the regular propositional core, and we augment it with existential quantification. We have this conjunction, very similar to a separating conjunction that we call outcome conjunction. And then we have these two primitives for reasoning about weighting functions. So to just get an example of these new assertions that we introduce, let's first take a look at this bottommost primitive assertion, where you can think of P as a sort of a program property specifying a set of program states in which the property may hold. And it is lifted with a certain weight from our semi-ring to hold on weighting functions. So in this case, you can intuitively view this definition as any weighting function that satisfies this assertion. Well, the outcomes of this weighting function must satisfy P with the total weight of A. So to get a better visualization of that, suppose we have this property P consisting of these two program states. Then considering this example weighting function, we say that it satisfies P weighted with A if first the non-zero support of this function falls in P. So we can see in the red bars, sigma 1 and sigma 2 are fall in P. And if the total weights add up to the weight specified, which is A. So the next primitive assertion that we have is to support divergence. So this is very, very similar to the weighting of program properties, except here we essentially, any weighting function that satisfies this assertion must diverge with a weight A, and it must only diverge. So this essentially consists of a set of one single weighting function that looks like this. With all the weights on the non-termination outcome. And the last introduction we have is outcome conjunction. So for a weighting function to satisfy outcome conjunction, it needs to be able to be decomposed into a sum of two other weighting functions, each of which satisfies the wings of the conjunct. So to get a better visualization of that, suppose we have this weighting function m, and we say that it satisfies this outcome conjunction. Then we know it needs to be able to be decomposed into a weighting function m1, which satisfies the first wing of this conjunct, added to another weighting function that satisfies the second wing. And an interpretation of triples is follows the usual over-approximate sense, but recall that assertions in this case are lifted to weighting functions. And so as we will see, despite the fact that this interpretation of triples is fundamentally over-approximate, we can capture notions of correctness and incorrectness through it. So just to go through the subsumption of different program logics that can be done in total outcome logic, we know that partial correctness and incorrectness can be captured by outcome logic, whereas when we introduce support for divergence, we expand this to unify the entire landscape, including total correctness, and this naively named partial incorrectness, which augments incorrectness with some notion of divergence, not quite like the unreachability presented just before. So to begin with, let's see how we can encode these modal operators. So we have square p for representing that p always holds, and a diamond p modal operator that represents that p sometimes holds. To encode this as an actual outcome assertion in total outcome logic, we can provide this encoding. Very intuitively, this just says that for any weighting function that satisfies square p, it needs to either, its possible outcomes either fall in p or diverge. On the other hand, for the sometimes modality, we can encode it as such, where essentially we capture a backwards under-approximate notion of incorrectness by seeing whether the outcomes in the weighting function intersect with the property p. So these are the encodings of Hoare logic and the backwards under-approximate notion of incorrectness given by Lisbon logic. And these can be supported in outcome logic proper. But if we take a look at these encodings and we choose to transpose this allowance of non-termination in each of these modalities, we arrive at a slightly different set of modalities that we will represent as such. And what this ends up representing is that P always holds with no allowance of non-termination, and that P sometimes holds, or it may diverge. So just to give a unified view of the subsumption that can be achieved in total outcome logic, we see that with our support for reasoning on divergence, we can capture total correctness and total Hoare logic using this this alternative square modality, and we can achieve, we can capture a notion of, a different notion of incorrectness in which non-termination is treated as a bug in itself. And so in the case of a logic like Unter, which is specialized to detect non-terminating traces, this is basically just an instance of this diamond modality in which the program property we specify is simply false, by which we just specify that we're only looking for non-termination. Yes, sorry.
Okay, great. We can do one really quick, really quick.
I have a remark on the unbounded non-determinism, because you said it's non-continuous. It's not true in general. If you take traces, then the semantic is continuous. If you take relational semantics, it is not. And there is a mystery here that I not fully understand, why this abstraction goes from continuous to non-continuous. So just a little remark.
Okay, let's thank James one more time. Okay, and so for the last talk of this session, what was that? There's a little bit of hopefully the projection will work first try. Yeah, sorry. I was a little too eager. But let's see if the projection is going to work. Okay, looks promising. All right, wow, very lucky. Maybe. Okay, great. So for the last talk of this session, we have U-turn, forward-driven backwards analysis for incorrectness by Roberto Bruni. So go for it.
This talk was supposed to be the last one today, so I had to anticipate a little bit. And I think that by looking at the previous talk, I could skip half of it, because we have seen most of it already. This is a workshop on static analysis. We have been speaking about correctness and incorrectness, proving the absence of bugs, or trying to prove their existence, right? Oops, too much. And a duality that will be useful later on, observed by Peter, was that for correctness reasoning, you get to forget information as you go along a path. Is it working? Yeah. But you must remember all the paths as you do the computation. Instead, for incorrectness, typically, you remember information as you go along a path. You will find it in the post, but you can forget some of the paths. You can drop disjuncts. And our goal was to define a reasoning framework for incorrectness that aims to expose reachable bugs and also their origins, their source of errors. So for collecting semantics, we have seen it already. We can account for non-deterministic behaviors. We try to move here. Yeah. And so in general, given a source state, we can reach many target states, or we can also diverge. And the collecting semantics is seen as a function from the source states to the set of possible outcomes, which can then be extended by additive lifting to the power set of states, right? And we have seen already how OR correctness and OR incorrectness can be expressed through the collecting semantics as in terms of an over approximation of the outputs or an under approximation of the outputs, right? For this talk, I'm going to use another semantics, which is just the opposite of this relation. That is also known as the weakest possible prey by OR. It is different from the weakest liberal prey and the weakest prey that we've seen before. Essentially, for a given output, for a given target state, it tells us what are the possible source state leading to it. And using the weakest possible predicate transformer, we can express the necessary precondition logic as an over approximation of the backward semantics. And Lisbon triples or sorry, I have to redo everything. Yeah, there is some delay. When I press the button, I need to wait a few seconds. So let me do it straight here. Yeah, there is maybe some interference. I don't know. So this is known as Lisbon triples. It is known as BUA, and it is also known as sufficient incorrectness. I will stick to this name because I'm going to reuse the inference rules from this presentation. Let me use this. So you see the 4 logics I'm speaking about can be described by this taxonomy. And we will focus just on the incorrectness analysis side, so the bottom part of the diagram. And the aim of the 2 logics is slightly different. Incorrectness logic and their derivatives are aimed to expose reachable bugs. That's what they have been designed to. While sufficient incorrectness logic or backward under approximation semantics aims to expose sources of bugs. So source states leading to some error in the end. I already classified this logic as a forward logic, and this is also observable at the level of the inference rules of the logic. I will go briefly through some of them. For the sequential composition, this is the classical one. For non-deterministic composition, from the same source states, you can reach Q1 by executing C1, and you can reach C2 by you can reach Q2 by executing C2. Then, by the non-deterministic composition of C1 and C2, with the same input, you can reach both Q1 and Q2. Right? And for the assignment, we can only use the Floyd axiom for assignment. The OR axiom would not be valid for incorrectness. And this one, as well as this one, makes it evident why it is a forward logic, because the rules are applicable to any precondition when you try to infer the postcondition. Let me also point out that for incorrectness, you can always have the false postcondition that will give you a valid triple for any command and for any precondition. And by the combination of this fact and this rule, we can drop some disjunct in the inference. For example, we can forget about the outcome of C2. Okay? And so in the tool developed from incorrectness, you may design different heuristics that tell you which path to drops at which point. For the sufficient incorrectness logic, the aim is to expose the sources of bugs. So it works backward. You imagine you have the postcondition and you want to infer some precondition that explain why the bugs are produced. For sequential composition, you have the same rule as the previous one, meaning that you can use it in both directions, in a sense. For the disjunction, for the non-deterministic choice, you may have different ways of producing the same output, and you collect them. And for the assignment, instead of using the Floyd axiom, you can use the OR one that is applicable to any postcondition. But in this case, also the Floyd axiom would be valid. And dually, now we can have false as a valid precondition for any command and any post. And the dropping of disjunct happens by moving backward. So we may decide which source to track when we have many variables. Okay, so let me come to the core of the contribution. We aim to combine incorrectness reasoning with sufficient incorrectness logic. And you see there is a semicolon here because we do this in this order. We compose them in this order. So the idea is to first prove that some bugs are reachable, starting from some precondition. And incorrectness logic will provide us with a guarantee that there are no false alarms this time. And then, taking into account this information, we exploit the sufficient incorrectness logic to trace back the precondition leading to those bugs, okay? Which in general will be a subset of the original preconditions. And the key idea is that in doing the backward reasoning, we will re-exploit the forward reasoning, the proof that those bugs are reachable. And so once the name of the presentation, we move forward with incorrectness logic, we find some bug, we turn back, and we try to detect the sources of those bugs. And so this is the overall idea from the technical point of view. Imagine that you have given a proof of incorrectness logic that this triple holds, and you have the whole derivation tree of it, where Q is some bug. Our judgment, building on this proof, will try to infer a precondition P prime that would be a subset of P, such that any state here can lead to some bug in Q. And this will be done inductively on the command C, of course, but also on the proof of incorrectness. So the inference rules are like this. So we have here, imagine a proof of incorrectness for a composition of two commands. And inductively, we look for the bugs that are reachable from the execution of C2, starting from some R1 that is a subset of R. Okay? Here we could start with Q. In general, the rule works with any subset of Q. We can focus on some bugs. We don't necessarily need to account for all of them. Once we detect R prime, we can reuse R prime will be a subset of R, and therefore we can re-exploit the previous proof of incorrectness for C1 to deduce P prime. This will allow us to conclude that starting from any state in P prime, by executing C1 and then C2, we can reach some of the bug in Q prime. Here is another example about the dropping of disjuncts. Maybe we have a proof of incorrectness that only cares about one of the branches. And so in order to derive the source of the errors, we will only focus on that branch. And we forget about C2. So the incorrectness proof that we made forward will be exploited when we are reasoning backward to decide which path to drop. Okay. And then for the assignment, just as another example, maybe we have some postcondition for the assignment obtained by the Floyd axiom. We can focus on some unwanted states of this postcondition that are errors. And then we apply the OR axiom to filter out those states of P that can produce those unwanted states. To conclude, here is just a simple faulty programs. It's a toy example and a doc one. So imagine that we init some array with length L, then we change the value of L, and then we compute again the length of the array. But unfortunately, the init function is wrong because for some values of L, for example, when it is 2, the initialization procedure forgets to insert the null value. Okay? And therefore, when we will try to compute the length, we will get into some error, right? We will try to access a part of the heap that has not been allocated. So using incorrectness logic, we may infer, starting from any precondition with no assumption on the initial state, for any state, that some error can be reached. Okay? And we get maybe a post-condition that is not immediate to understand. But then exploiting the proof of incorrectness and our system, we can infer automatically the proof that the precondition leading to the error is when L is equal to 2. So any state where L is equal to 2 will lead to that error condition, which is much simpler as an information to provide to the programmer with. So to conclude, in this work we try to integrate, to combine two different logics of incorrectness, of under-approximation. And one is moving forward and the other working backward. We could also dualize the approach, so starting from a sufficient incorrectness logic proof, and then derive a corresponding incorrectness logic proof to show that some bugs are reachable, which one, out of a larger set. And so in the end, we can say that the whole, the combination of the two, is more than just the sum of its parts, because in doing the second analysis, we can re-exploit what we learned from the first one. As a future work, we would like to integrate this approach with abstract interpretation and possibly with B-abduction strategies. And this was the take-home message that I prepared for the end of the meeting, but I will present it to you now. So you see that sometimes when different approaches are proposed, one tries to fight to say mine is better than yours. We can redo everything that was done before. But in general, my message that, as also many other talks already shown, that by combining different approaches, we can gain some more information.
Okay, great. So again, we'll do one quick.
Everyone. The funny thing is that in abstract interpretation, when you do static analysis, we do forward, post, backward, pre. But when you go in the abstract, if you iterate forward, backward, you get results that you cannot do with one forward,
the other,
backward.
yeah.
Have you the same phenomenon in the logic?
I think so, yeah.
Okay, so you iterate and you write another paper.
Yeah. It's a good point.
Okay, great. So let's thank the speaker one more time. And now we have lunch. Did you want to say something? Okay, lunch on level 3, and we'll see you back here after lunch.
Okay, let's kick off this first afternoon session of TPSA. We're starting with a talk given remotely about compositional shape analysis with shared abduction and biabductive loop acceleration. And Florian is giving the talk. Hey, Florian, we can't hear you yet, sorry. Just a sec. Calibrating blasters. Nope. Unmute. Try. Yes, go ahead.
Filter out unsound candidate triples, that's the contracts, has been a thorn in the side of any biabduction practitioner since time immemorial. This 15 years ago. And we absolutely agree it's not great, and we therefore set out to make our tool Broom sound in a single phase, and we actually achieved this without changing the logic, the biabduction procedure, or the abstraction procedure whatsoever. And therefore, our techniques are actually completely generic and can also potentially be used in other analyses or other analyzers as well. But before I get into what our techniques actually are, let me give you a quick introduction what the unsoundness problems actually are that we need to solve. The first one can occur if we have simple branching. In this function choice, we take two pointers and non-deterministically read from one of them and return the value. Now the question mark here is essentially a non-determinism operator, which can stand for something like file input, network input, user input, you name it, right? Something that cannot be described in terms of the actual parameters of the function. And we as humans see, well, this function is only memory safe if at the function axis both pointers are allocated, aligned, not null, you name it. Now let's have a look at what the analysis will do. In the beginning, it will start with a precondition just saying top. So we don't have anything yet which we need to compute, or which we need to be memory safe until this point. Then we do a step in one of the branches, and therefore we need to load from, in this case, for example, P. So we need to have P to be an allocated pointer, it needs to be aligned and so on. So we just say we need the points to predicate for P in the precondition. And similarly, for the other branch, we get the same thing with Q. Now the analysis will say, okay, I found two potential preconditions, one with P, one with Q. Let's have a second phase and check whether these are sound. And unfortunately, as we already noticed, they are both not sound. So in the end, the analysis will not find any precondition or any contract for this very simple function, which is not great, right? And this is something that has already been described back 15 years ago in the first paper about biabduction. There, the authors didn't really find a good solution other than the second phase, but they at least figured out that a heuristic combination of candidate preconditions might cover some of the branches. But that's not enough to get rid of the second phase, right? More recently, the triabduction idea that was developed for the outcome separation logic was introduced as a bit more of a foundational idea to actually solve this problem. Essentially, now we don't have two sides of the biabduction operator, but now three sides, and we try to compute a single precondition for both branches at the same time, which is perfectly fine, would solve the problem, but is unfortunately a bit unfeasible in our specific use case, since it would mean to implement completely new reasoning mechanism on top of our existing biabduction. And so we took a step back and looked at the problem from a different angle. Because biabduction as a reasoning technique is sound. We find the correct preconditions. We just don't share them with all the other points that are equally reachable from the same precondition. So what we therefore developed is our new technique called shared abduction. And the main idea here is that compared to before, where we only have a precondition formula and a current state formula, we now have a single shared precondition formula with potentially multiple current state formulas at different program locations. And it works like this. If we then do a step in the analysis, we'll once again find out that we need the points to for P. We will therefore add it to the precondition. But at the same time, since both the branches are equally reachable, we also add it to the other part of the other branch. And similarly, if we find out that we also need Q to be allocated, we also add it to both the precondition and the other current state formula. And therefore together we get the correct and expected precondition of both pointers and the expected postcondition of a disjunction of the two results. And this is a very easy but very powerful idea that works also for arbitrarily nesting of branching, for deterministic and non-deterministic branching interleaved, you name it. So have we solved all problems? Unfortunately not yet. There's another problem with unsoundness, and that comes, as we've heard before a little bit, if you have loops and want to do abstraction. Now if we look at this very simple function here, traverse even, it traverses a linked list with two nodes at a time. Okay, this is not very realistic, but it's a very simple example that we should be able to handle, right? Okay, let's have a look. What does the analysis do? We start again with top. We'll find in one step, after entering the loop, that we need one node of the list. And then another step, another node. Okay, now we're back at the loop head, obviously. Now we don't want to find infinitely many nodes. We want to do some widening, some acceleration, some abstraction. In this case, for example, we could see, okay, two list nodes together make something like a list. So let's exchange it for the abstract list segment predicate, going from X to some L2. Now, unfortunately, this list segment specifically does not encode the length of the list. But as we've seen, the function actually traverses two nodes at a time, so it's only memory safe for lists of even length. So this immediately is unsafe as a precondition. Now, unfortunately, the analysis will not ever figure this out, or at least not yet. It will try to find out, is this now a fixed point of the analysis? So it does another while loop iteration, and then it does a second phase and only finds out then that actually this does not work. So what is the problem here? Is it that we should be able to encode even length lists? Is it that the abstraction should be better? Not necessarily, I'd say. Actually, we can find similar examples for pretty much any kind of logic and any kind of abstraction operator. So that's not really necessarily the solution to the problem. That we actually, or it can be a solution to this specific example, but not in general. So what we actually want to have to get rid of the second phase is a way to figure out immediately that we have reached a sound fixed point, essentially a loop invariant, instead of just a fixed point of the analysis. So our idea is now to use biabductive loop acceleration with 4 steps. The first one, just compute or just analyze the loop once. The second one, use a heuristic to compute a candidate invariant. The third step, try to reductively verify this invariant. If it fails, we fail early. If it succeeds, we can, in the fourth step now, actually construct a loop fixed point, or a fixed point of the analysis for this loop, which is guaranteed to be sound. That's the basic idea. Let's have a look at what this means for this specific example that we just seen. Once again, we have the 2 list nodes, which we get from the analysis. Now, as we've said, list nodes kinda abstract 2 lists. And specifically, if we want to figure out a loop invariant, we kinda need to figure out that we are at some point while traversing the list. So let's say we have a list segment from the original value of x to some location L, where x is currently at L. And we might have some remaining list up to null because we ignore cyclic lists for now. And with this idea, we can then construct our invariant, or our candidate invariant, by just saying, okay, in the precondition, we have the 2 parts, which is something that we need as a precondition. In the current state, we've already traversed from the uppercase X to L, that is the blue part. It might contain some changes, something like deallocation or so on. In this case, it doesn't. And we still need to go from L to null. And that's essentially the idea for the invariant. Now, deductive verification will just enter the loop once again. It will assume that L is not null, which was the loop condition. And therefore, we immediately know that the list segment from L to null cannot be empty. And so we immediately can get a single new node out of it, which we call L prime. But unfortunately, now we can't get a second node out of it, which would allow us to actually verify 2-step example, which obviously we can't. And therefore, we can immediately fail fast. Now, if, however, would assume that the function actually only does 1 step at a time, this would already be sufficient to show that we have reached, or that we were able to get through the loop. We can now do abstraction once again, fold the list, the extra node into one of the list segments, and essentially get back the invariant, and have shown that the invariant actually is an invariant. And with this, we can then actually also succeed fast by just constructing the fixed point of the analysis as given a list from x to null, it will return a list, same list from x to null, and the program variable x is now at null. And that's essentially the whole idea, really to just make sure that whatever we get out of the loop for the analysis is actually sound. We will not always succeed. The heuristic in this case will probably be very similar to what we used before for the abstraction. But we are a bit smarter because we now directly check whether it actually is sound. And as you've seen, we not only fail fast, but you also succeed quite fast. And this actually improves the runtime of our tool Broom quite significantly. So we have implemented our techniques as proof of concept techniques, which we call now the brush analyzer, compared to the Broom analyzer, which is the old one. So the x-axis is our new tool, or the tool with the new techniques. The y-axis is the old version. And as you can see, most of our experiments, which are sometimes handcrafted, sometimes from our own small benchmark, are above the equal timeline. To be more precise, overall, we almost reduced the runtime by 50%. For loops, or programs with loops, we actually reduced the runtime by 95%. Primarily because we reduced the amount of analyzed loop iterations by 66%. That's just the second phase, and the speed up in the first phase. As you can see also, the branching part is not that much faster, primarily because the branching examples in this benchmark set are all deterministic, since Broom cannot handle non-deterministic branching, so that's just a cherry on top. And yeah, that's essentially what we get out by just adjusting the symbolic execution of our analysis, and not the logic, not the by-abduction procedure, not the abstraction procedure. And as you might have noticed in the beginning, the title was Extended Abstract, since this paper, or like the work for this paper, or the work that I just described, will be published as a paper at ESOP later this year. So if you want to have a look at the full version, please go ahead. That's it from my side. Thank you for your attention.
Thank you, Florian. Any questions? No. I have a question. In your new by-abduction technique, is it as complete as the original one? Because suddenly you can only by-abduce specs of a certain form because you coalesce those pointers.
So we have not changed anything about by-abduction itself. So the reasoning technique is really the same thing. And for the branching example, any program without branching and loops will be completely the same. With branching, we can now additionally handle non-deterministic branching. And for loops, our heuristic is essentially the same as before, so we can handle at least the same amount of programs. Just some that might time out can be now handled because we're now faster. So we are just strictly better. We can handle the same things as before and some more.
Cool. Well, thank you. Okay, next up, Lorenzo Gazzella will talk to us about calculational design of incorrectness separation logic.
Okay, thank you. Today I'm going to present our ongoing works on systematic design of incorrectness separation logic. It is a joint work with Roberto Bruni and Roberta Gori. So we start by defining the problem. The problem is that often proof systems are designed ad hoc for a specific semantics. So we set the theory of the logic, and then we try to set up the inference rules ad hoc for that theory. But this could be challenging, and there is no guarantee that we obtain a well-designed proof system. One approach that has been proposed is the calculational design by Cousteau. That gives a general recipe to derive a proof system for correctness and incorrectness analysis directly from the semantics. The problem is when we deal with heap manipulating programs, we don't have the locality principle that is the core of separation logics. In fact, in separation logics, we would like to have axioms that focus on the minimal amount of information and to derive, to execute the command. And then with the frame rule, we would like to enable the scale of the reasoning. So for example, in the axiom on the left, we have that P skip P as a global precondition. And in separation logic, we would like to have axioms like in the right axiom that focus on the discrete amount of information regarding the heap. So we get emp skip emp. That is the axiom of incorrect separation logic. So our contributions is first we design a systematic design of program logic. And so by exploiting some closure property of the semantics, that for example could be the additivity, the weakening, and the strengthening of the precondition, postcondition, and the locality principle, we derive the axioms of the logics. So with this approach is that we justify or we improve some existing ad hoc axioms. And then for the case of manipulating program, we have axiom that focuses on the minimal amount of information for that specific atomic command. And then as a last step, we derive a more inclusive set condition for the frame rule. The second contribution is the application of this systematic design to separation logics. And the first one is the under approximation logic, and we apply it to ISL and its concurrent version. And we improve the expressiveness of the proof system. And then we are trying to apply the systematic design also to over approximation logics, but it is an ongoing work. So the systematic design follows some steps. We first define the semantics of the logic. Then we identify some closure operators. And each closure operator induces a partial order. And the meaning is that an element is smaller than another one if we can recover the second one, starting by the first one, and using some closure operator. And then we define a notion of minimality induced by the closures. And so we take every partial order, and then we take the closure, the transitive closure. So the minimal element of this order will be the axiom of the logic. And the inference rule will be derived from the closure of operators. So we see now the application of under approximation logics. So we set the theory of our logic that is parametric to the program semantics and to the command, the basic command C. And we say that the theories are the set of valid triples PCQ, where Q is an under approximation of the semantics over P. And then we identify some closure operator within the logic. The first one says that if Q and Q prime are an under approximation of the semantics of C over P, then we can remove Q prime and add any P prime and get a valid triple. And this is usually embedded in some existing proof system with the consequence rule. Then we have the second one, that is the one that is embedded with the disjunction rule. And the last one, that is the framing. So we can add, if we have a valid triple, we can add any frame to that variable, and we will see later what is a frame in our setting. So each of these closure operator induces a partial order. And for example, we take the triple PC, Q and Q prime smaller than the one on the right, because by applying the consequence, we can recover the right one from the left one. And so the axioms will be the minimal elements of this order. For that specific case of under approximation logic, we have that any finite application of frame, disjunction, and consequence can be transformed in a composition when we first apply the framing, then the disjunction, and then the consequence. So suppose to have a sequence of closure application in any order. We can transform the application by applying first the the frame rule, then the disjunction, and then the consequence. And so by transitivity of the order, we can just apply each of the closure operator only once. And for this reason, we can define a relation that in one step summarize the transitivity closure of the union. And we get this new order that says that a valid triple P1 CQ1 is smaller than another one if we can find a frame that we can add to P1 and Q1, and if we can find a valid under approximation triple that we can add to P1 star R, and then P is the triple on the right can be recovered by the consequence rule from the left one. So the minimal element of this new order will be the axiom of our logic. We see now what is a frame in our setting. We define an heap as a partial function from location to values with bottom, and the store that is a total function from a set of variables that are the program variable, and then a set of auxiliary variable. Then the state is any pair of state and of store and heap. And then the possible frame that we can use are those that does not constrain the program variables. So informally, what we express is that the frames can only predicate on the auxiliary variables. And the auxiliary variables are never modified by the programs. So what we get is a semantic proof system that says that any minimal triples is a valid under approximation triple. And then whenever we have a valid triple, we can add any frame that we take from the set that we defined before and still get a valid triple. Then we have the disjunction and the consequence that are derived by the closure operators. And this construct a sound and complete proof system by construction. So the setting is parametric to the semantics of basic command, and here we take the semantics of ISL. And what we get is that for this, here we have a slightly different meaning for the assertion emp, and it says that we have a memory is the set of every memory with an empty heap, and where for each program variable we have a primate variable that is equal to the variable x, and so we get this is a subset of the derived proof system. For the skip, for example, we start with an empty heap, and then by executing skip we get an empty heap. And for the allocation, we start with an empty heap, and by allocating x, we have that x is pointing to something. Then the frame rule says that we can take any frame that does not speak about auxiliary variables. And then we have the rule of exist that we see now. So we see now that the frame rule on only primate variables can constrain also the program variables. So here we have this example. We start with x equal to x prime, and then we execute the skip. We apply the axiom, and we get x is equal to x prime. Then by the framing, we add that x prime is equal to 5 to both sides. And then by the rule of exist, we remove x prime, and we constrain over the possible program variables. And this is a triple that we can derive in our proof system, that it was not derivable in ISL. And this because when we execute when we execute this command, we cannot frame out the heap that is speaking about X, and so we cannot apply any of the axiom. Then we try to apply our systematic design to the semantic of the concurrent version of ISL. And since it lies in the theory of under-approximation logic, with a slightly different notion of the store, that is a partial function like the heap, and so as a consequence, a different notion of the separating conjunction. But what we get is that we can reapply the previous methodology, and so, for example, what you get is that for the allocation command, in the original proof system, we have that in the post condition, we have an existentially quantifier only over the possible location. And of course, since we don't have an infinitary disjunction rule for this is a source of incompleteness. And the axiom that we get by minimality, it also quantifies existentially over the possible values that the variable X is pointing. So what we defined is a general methodology that is applicable to different semantics and assertion languages, and that can give some feedback on existing proof systems. As a future works, we would like to explore the over-approximation logic, to apply our strategy to over-approximation logic with local reasoning, and to use abstract interpretation to account this procedure. And then finally, we would like to apply our methodology to logic for backward reasoning. And thank you for the attention.
Okay, we have a few minutes for questions. Patrick?
So, in your completeness proof, you must exhibit what are the auxiliary variables that you need somewhere, because you say there exist auxiliary variable, but should I take 142? And so the completeness proof must give you the necessary auxiliary variable. And can you characterize that?
Yes, but we assume that we have an infinite amount of auxiliary variable, and the axioms are set to be equal to the program variable. So I think that it characterizes the possible auxiliary variables.
In the proof, there cannot be infinitely many auxiliary variables in the end.
But they are bounded from the program variables.
Yeah, there's one for each program variable, right?
Yes.
Any further questions? We still have 1 minute. Radu?
There were a bunch of talks earlier that presented other logics. Did you feel that you could apply your methodology for any of the ones that you saw today?
I don't know. Hopefully.
Okay, thank you again.
Thank you.
the HDMI roulette again. Okay, and now Pedro, is it? Yes. Is going to talk to us about scalable bug detection for internally unsafe libraries. I knew that was going to happen.
Okay, hello everyone. What I'll be presenting.
It's good? Yes. Okay, it's good now. Okay. So we focus on allegedly safe libraries that rely on internal use of unsafe code. And our main motivation for this is the Rust programming language. So Rust offers a type system that statically ensures memory safety, making it a safe alternative to C, C++. So although Rust does provide a way of performing low-level unsafe memory operations, it still ensures memory safety through the use of safe abstractions. Now, for example, here we have an abstraction of even numbers in Rust. So we assume there's a user-defined even type. And we have three functions. We have a zero constructor that basically wraps 0 as something of type even. We have a successor function that receives something of type even, increments its value, and returns it as something of type even. And we have a next function that receives an even number, increments the number twice, and returns it as an even number. Now, as you can see, the successor function doesn't really respect the abstraction that we want for even numbers. So the type of the function is marked as an unsafe function. And when we look at the next function, since it uses the successor function, it wraps its usage as inside the unsafe block. But the next function itself is a safe function because it's using this unsafe successor function in a safe manner by calling it twice in a row. So this is what I mean by using safe abstractions to basically encapsulate usage of unsafe code. And we can say that this is a safe abstraction for even numbers because as long as we interact with this library using only safe functions, then we are guaranteed to never break the assumptions that we can do on elements of the type even. So, for example, I could define this naive function that receives an even number, and then it basically checks the remainder of the division by 2 of whatever it was passed as an argument. If the remainder is 0, then it's an even number and it does nothing. If it's 1, then it will unsafely perform some operation that results in undefined behavior, like division by 0 or performing a double free. Now we can be sure. Now the naive function is marked as safe, and we can be sure that the function is safe to execute as long as we only use safe functions from our even library. And we can ensure this even though we have usage of unsafe code inside, because it will never reach the if block. And this is the main idea behind the type system in Rust, that the type signatures in Rust actually encode specifications. So, and we can do so by basically restricting the inputs that the function takes by assuming that as long as we have well-typed inputs, the function will execute safely. If, for example, we were to consider the successor function as a safe function, then this would no longer be a safe abstraction because it breaks the assumptions that we are trying to make about the even type. So the naive function would be able of exhibiting undefined behavior, even though it is marked as safe. Now, what's special about Rust that we don't have, for instance, in C language is precisely this treatment, this separation between safe and unsafe code. So this here is an equivalent C code to the abstraction that we have for the even type. It's mostly identical to the unsafe abstraction in Rust. And the key idea here is that in C, since we don't have this notion of unsafe functions, every function in C is assumed to be an unsafe function. So we cannot just look at the type signature and say that the naive function is incorrectly typed because it will exhibit it might exhibit undefined behavior. The C-type system always allows that to happen. In C, the only function that is enforced to be safe is considered to be the main function. So if we want to find these kinds of bugs, we need to consider that there exists an executable trace that starts from the main function and eventually calls the naive function with an incorrect input. So to sum this up, the idea here is that in Rust, when you have a safe function, as long as we have well-typed inputs, we will never have undefined behavior, or we should never have undefined behavior. And in functions in C, they're by default unsafe, so undefined behavior is always possible. So we can't really prove these kinds of bugs looking just at the type of a function. So what this means is that while in C we have, for us to detect these sorts of errors, we need to have an executable path from a main function. In Rust, we can look at functions isolatedly, and we can report errors as a type unsoundness for that given function. So we don't really need a code base as we need in C to verify to show that these bugs exist. We can actually find these bugs in arbitrary Rust libraries. And for those who are familiar with the term, this basically means that the notion of manifest error is much larger in Rust than it is in C. And so, in terms of reasoning to show that the safe encapsulation is in fact correct. So there's both automated and foundational approaches. Most notably, Rust Belt provides a framework to perform machine check proofs in the rock proof assistant for these kinds of cases. All of these are consistent correctness proofs using Hoare logic or derivatives. And therefore, these approaches are over-approximate, and they rely on type invariants that are basically a semantic interpretation of what it means for a value to be of a given type. And these type invariants must be user-provided. Now, in terms of refuting the safety of these allegedly safe libraries, because there's no guarantee that they are in fact safe, there is no known work about this, and this is what today's talk is about. So I'm presenting our approach Rust, which fully automatically detects these types of this kind of type unsoundness in allegedly safe libraries. Our approach presents proofs of incorrectness using incorrectness logic. And instead of relying on user-defined annotations and type invariants, we work with under-approximate types. So let's consider the unsafe abstraction in Rust, where we consider the successor function to be a safe function. So here the idea is we have the blue box that represents the type space for the type even, and we're going to symbolically execute these functions to try to populate this type space. So the zero function doesn't receive any arguments, so we can symbolically execute it, and since it's a safe function, its output type, whatever it outputs, must be of the type even and must satisfy the even invariant. So we know that 0 belongs to the even type space. And since 0 is a well-typed instance of the even type, we can provide it as a well-typed input for other safe functions. We could provide it as input for the successor function, and we would know that it's, after executing it, we would know that 1 must be of the type even. We could pass 0 to the next function and see that 2 is also of the type even, and we can continue for as long as we want. Now, this also means that for the naive function that is supposedly safe, we could provide any well-typed input, and the naive function will execute safely. But as we have seen before, if we provided an odd number, then the naive function will result in undefined behavior, which by the type signature should never happen. So we have shown that there is a type unsoundness in our library because basically what happens is that we can only with safe calls to the functions in our library, we can actually construct a program that results in undefined behavior. So we've seen that example. We can construct this program as well. We first learned that 0 is something of the type even. Then we call next, and we learn that 2 is of type even. We call the successor function. We know that 3 is of type even. So the naive function will exhibit undefined behavior for 3. We could have a similar program where we switch the successor, the order of the successor and the next function, where we first infer that 1 is of type even and 3 is of type even, and both of them will result in undefined behavior. And the important thing to note here is that although we have proven that there exists a trace in a library, that the safe trace in a library that will result in undefined behavior, we are not exploring the space of all possible traces. So in these two examples, right before we reach the call to the naive function, in both partial traces, we infer that 3 is of type even, but we do not explore the traces from there. We don't, so we don't go from the first partial trace and branch out from there, or try to branch out from this from the other program. In both programs, we managed to learn that there exists they learn the same instance, that 3 is of type even, and we test out on that inferred instance. So this is to say that our approach shortens the exploration space, which we expect to be an important factor in terms of the scalability of our approach in the future. So looking into the actual algorithm, so we start off by initializing an empty context for the type spaces, which we call sigma here. And then we pick some safe function from our library and some well-typed inputs from what we have learned so far. We symbolically execute the function for those inputs, and if we get undefined behavior, then we manage to refute safety of the library. If we have no undefined behavior, then that means that we learned a new instance of the type, so we can update sigma accordingly. And we repeat to the second step to pick another function. The algorithm terminates either when we get undefined behavior or when a limit is exhausted. So this means that we can get false negatives. So some type unsoundnesses may not be found, but we obtain no false positive guarantee, which means that every refuted type that we get is evidence of a type unsoundness in a library. Yes, and at this point, we have a prototype implementation in OCaml for a very simplified version of Rust, which we call Lambda Rust, since we are mostly inspired in the Lambda Rust language by Rust Belt. We don't handle any references yet, which is an important thing about Rust, but it is part of our roadmap. We have a full formalization in Rock of the semantics of our Lambda Rust language, as well as the logical framework, which includes basically a simplified version of Rust Belt and an incorrectness separation logic and properties relating both kinds of reasoning. And we have a partial implementation of the algorithm itself, though the interesting properties that we want are still a work in progress. And do I still have a minute or two? Okay. So I'm going to quickly just show a demo.
Bigger, please.
Bigger, okay. Maybe too big. Okay, so basically I have here an embedding of our even example using our Lambda Rust language, but in OCaml. So here we have the 0 function, we have the successor function, we have the next function as well, and finally we have the naive function. And down here we have our algorithm, find unsoundness, that basically if we run the algorithm, it found no unsoundness because I set the successor function as an unsafe function, which makes sense. If it's unsafe, then there is no unsoundness to be found. But if you make the function safe, then the algorithm found the unsoundness, and so we can be sure that, and like I said, this is a true positive. It's a guarantee of the algorithm, so yes, that's basically what I wanted to show you. So yeah, thank you for having me.
When you say symbolic execution, it's on the types.
Symbolic.
When you say symbolic execution, it's on the types.
I mean, we don't really handle types, or better yet, the types, we only have a name for it. So we symbolically execute, like we have the state, we execute it, get the state, and then we learn that whatever state we get at the end must be something related with the output type itself.
Okay.
That's the idea. Okay.
Any questions? I have a question. You
Yes.
say if you find a problem, then it's because there's an unsoundness in the library. But
Yes.
it could be, I have trouble figuring out how you delimitate the library versus the rest. Like it could be a problem in some other library that's unsafe and exposes unsafe types somehow. Like if okay, so there's a problem somewhere.
Yeah, yes.
Hi, thanks. That sounds like a fun tool. So do you have, I don't know, ideas or plans for finding bugs that only arise when you combine two libraries which are correct in isolation, which is a particularly fun kind of thing that sometimes happens?
This works with different types. So basically what's going to happen is that you populate those two types. And since you're only handling safe functions themselves, like if you find undefined behavior at some point, it means that there exists an error somewhere. We don't know, you don't know which type it is, but this generalizes for more than one type, if that answers the question.
Okay, so is the plan like that the standard library types might be axiomatized in or something, because I can use those as well? Right, like, I don't know, maybe a library uses vec of even or something, and now it's relevant what you can do on the vec.
Oh.
And things like that.
Yes. Not sure how to answer that question. Do you have any idea?
Vec and we generate the spec of vec. You can just do that same thing on vec and get what a vec is.
Right, so this would be like the tool would come with these descriptions or something, is the idea.
You just run it on the standard library,
right.
and it will infer the type space for vec.
Right, well, I would have to run it on my library combined with the standard library. But
well, we would, yeah, probably pre-run it or something.
Yeah. Okay, cool, thanks.
Okay. Another. There's more people there. Yeah, that's fine.
So I want to ask the question that I thought Ralph was going to ask, which is, so with the sort of Rust Belt work, they found bugs in the unsafe library.
Yes.
Now, have you got enough that you can find those bugs, or is there other technology that means like higher order or something that you're not there yet?
I mean, I'm not entirely sure. Like, I mean, we don't since we don't handle references. There are a lot of bugs that we can't find. For instance, like, I think iterator invalidation, that was one of the errors that they managed to find. Like, that's something that you need to handle. Reason about references, I think. Not, yeah, but yeah, we haven't looked at actual examples that they managed to prove in the. Actual errors that they found in the standard library, we just came up with like these simple examples that we managed to find. But that is something that we plan to.
No, it's a great pathway.
Yeah. Yes. Okay.
Thanks.
For that, okay. So, okay. Yeah, more trickier. Okay. Yeah. Yes.
Time for our next talk. So thanks again, Pedro.
Thank you.
Thank you.
Anyway, do you have sound?
Hello, can you hear me?
So our next talk is very dear to my heart. David will talk about specialization in infer. And slides.
Okay, let's start. So my talk is about interprocedural analysis. So let's present a bit the landscape here. First with a naive approach, context insensitive analysis. they will treat calls as just go-to jumps, and they will merge all calling context. So it's quite simple design, often very scalable, but also it leads to unacceptable loss of precision in practice. So another approach is global context-sensitive analysis. So here you keep track of the context in which each procedure was called. So it's a lot of context. And for example, here, you may come from 4 different chains. So you will have to consider all these situations. So the key features is that first, in this approach, you need to know where are your entry points. You start the analysis from the main function or any entry points in your code base. Also, with this kind of analysis, the callee depends on the caller and the caller depends on the callee. So there is a kind of cyclic dependency. It's not mandatory to compute in advance all the context. You can do that on demand, which is good. And also, for tractability, you can try to merge some context because sometimes you can reuse several call sites. And for example, with object sensitivity, you can reuse the same context for several call sites. And the third approach is compositional interprocedural analysis, where you express for each procedure as a summary. And what is a summary? It computes the effect of executing the function without assumption about its parameters. So now you will follow a bottom-up approach. You first compute the summary for the leaves, and now you are able to compute the summary for this function and this one and so on. So the key features now is that you can start from anywhere. And in terms of dependency, only the caller depends on the callee, but not the other side. You can still compute on demand your summary. But maybe you don't need all of them. But at the end, with this approach, you will have only one summary for each call site. So let's talk about Infer. So Infer is an industrial static analysis platform. We develop a lot of front ends for this platform. This is still a work in progress, never finished. With a lot of analysis also on the right that you can use with various languages. And Infer, it is used daily by thousands of developers, tens of millions lines of code, hundreds of code changes per day. So the key features is that we want to run the analysis on every code changes. And what is a code changes is just a fragment of the code base that has been modified by the user and maybe some dependency. So our approach to tackle such a challenge is to rely deeply on compositional interprocedural analysis. And our magic weapon here is to compute the summary formula. We use separation logic because summary is difficult to get right. Also, we have to do a bit of damage control. So sometimes we need to skip some functions. Maybe we don't have the code available for this function, or maybe we have some concerns with scalability. We have to make some practical choices. And another example of practical choices is that we don't want to rely on a global fixed point. So if we hit a recursive call, this second call will be considered as unknown. And at the end, the strategy we follow is named on-demand bottom-up summary computation. So let's see an example. So you have this function, f, in class A. You don't really know its color. You don't care. We will start from it. It makes a static call to b.j. Okay, it means we need to get a summary for j. But in j, we have 3 calls. For the first one, we compute a summary. We use it. Now we consider the second call to d.e. We compute a summary. We use it. We continue. And now we realize that we already have a summary for h, so we can reuse it locally. And every time we use a summary, we do what we call applying a summary. This is where compositional system works, and you get all your information. Okay, we are done. Now we have the b.g summary, and we can end the analysis of f and compute the final summary. So this is on-demand bottom-up summary computation. But what about non-static calls? Because in all my examples, all the calls were static. And in real life, you also have other kind of calls. So for example, you have virtual calls in object-oriented languages. So it means you have O.m, and you need to know a bit about the runtime type of O to really know what is the callee here. You also may have closures. So I've tried to put an example of closure in the syntax of Objective-C. It's really beautiful. So you are just applying a closure f, you don't know what it is, on 0. You may have function pointers in C. And our late backend is PHP, and this typed version, hack. And here you have this beautiful notion of late static binding, where you do this kind of static call, but in fact, it's a kind of virtual call on the object, on the class object. And this magic object really depends on the context where you have been called. So good luck understanding this semantics. But yeah, it's another kind of non-static call. And for this talk, I will focus on virtual call. So let's imagine you have this function foo. It does a very simple virtual call, O.m. But remember, we want to do a compositional analysis, compute the summary of foo without any assumption. And if we know nothing about O, we will have to consider all the possible runtime types of O. And in some situations, we have to consider a lot of disjuncts. We have to merge all of them in one huge formula, our summary. So this is why I called summary blow-up. It may be too big to really conservatively consider all this situation, and specifically with dynamic languages. So instead, we introduce this notion of summary specialization. So here is the idea. For each function, we will we may analyze it several times, but with various specialization keys. What is the specialization key? Well, it contains the only what the function and its transitive callees need to resolve their call. And most of the time, it's about runtime types. So given a specialization key, we will compute the specialized summary in 3 stages. First, we will add some assumption to the precondition, like field f of parameter x as runtime type C. Next, we perform the standard summary computation with the compositional analysis. And if during this analysis, for the current function or one of its transitive callee, some resolution failed, we will just remember that some information was missing, and this information will have to be explained in terms of the current function parameters. For example, I need to know something about field j of current object. So let's look at an example. We start from anywhere, a.f. It makes 2 static calls. So we need to compute the summary for b.j. With b.j, we start with simple static calls. But when we hit the virtual call here, we need to know the dynamic type of x. So sorry for the notation, but this is a virtual call, and the receiver is x. big A is just a type information. So yeah, we don't know what is X because it is a parameter here. So we stop, in a sense, and we ask for specialization. So we ask F, hey, do you know the runtime type of X? And if it knows it, we will use this information to compute again this summary. And this time we assume something extracted from this information here. This time we can resolve the virtual call and compute one first summary. This is our first specialized summary. So we are back to F. We continue here. We have another call to B.G, but in another context. So first we ask if the caller knows something about runtime type of X. If it was C, we could reuse the previous specialization. But here it is not the case. So it's another specialization key. And we assume again something new. And this time we resolve differently the virtual call. And we are done. So at the end, we have performed two analyses of the same function. So this is not the same compositional approach as before.
But how do you know the runtime type?
Well, either you have enough information here, or you ask it from your own caller. And if you don't have a caller, you stop there. This is not complete. Yeah. We have been using this approach in Infer for 2 years now. We have to be practical. So sometimes we may have too many specializations of the same function, so we need to bound the number of specialization. We also have to accept some time overhead. But what is nice is that with the same approach, which is this specialization about runtime type, we can perform a lot of resolution. Not only virtual calls, but also closures, function pointers, and static let bindings. They are all managed in the same way. And we were also able to use the same approach to detect aliases between parameters. This is something classical with separation logic. And again, this is all in the same framework. So some experiments we did, especially about closure resolution, because we have a lot of closures in the hack code base. So what we did is we run the analysis on 7,000 files and some of their dependencies, but at the end you have a huge amount of files. We count the number of closure call sites that we reach, and we count how many of them we were able to resolve. So we were able to resolve 90% of them, and 40% of that is due to summary specialization. If you remove summary specialization, you still have 50% of resolution, but that's because sometimes you don't need to know your context. For example, here, you directly get the closure from the first call, and then you apply the closure. So in this situation, you don't need specialization. Okay, and as a conclusion, with this approach, it is enhancing of compositional analysis, but with a zest of non-compositional context sensitivity, just about runtime types. I think it's a nice workaround to avoid the complex notion of higher order summary. We were able to observe some clear impact experimentally. And we are currently using a lot this technique to tackle the challenge of statically analyzing dynamic languages like Hack and Python. We are using it in the context of under-approximation, which makes our life a bit easier. And we still need some work, both foundational and experimental, to make it work on over-approximating analysis. And that's all for me.
What is a summary? Is it
so yeah, in our case, it's under approximation, mentioning pre and post. So it's a relational approximation of your computation. Under approximation, yes.
I have two very small questions. The first one is, slide before that, you say that you... Oh, before that, sorry. that you have a time overhead of 40%.
Yeah.
Is that due to the fact that you analyze a lot more functions?
Yeah, because for many functions, you analyze them more than once. So this
Yes,
is
but
expected in a sense.
Yeah, but you're just analyzing more, so it's not an overhead. It's just more time of analysis because you find
Global
more things.
time, yes, for yeah.
So okay.
That's expected.
So it's pretty cool. And also, do you have a paper at some point? Do you plan on writing a paper?
We plan. For 2 years, we have been planning.
It's a big plan.
So stay tuned.
Thank you.
It's essentially lazy.
Yeah, and it's very important for us to be lazy because we want to be able to explore dynamic languages. So you don't want to make assumption until it is really, you have a proof that it is needed.
So yeah, so I mean, the example that you gave is with runtime type specialization. Is it like, I mean, it's more generic than that potentially, right? So what have you explored in that space?
Well, in dynamic languages, for example, I think in a dream world, you know the runtime type of everything. And now the semantic is very simple. It's very explicit. So that's why I found it useful to express everything about the runtime types. Because still you don't want to specialize on constant values, for example, because you don't need that. You can do constant propagation with compositional reasoning. So the idea is to use only the kind of specialization where compositionality fail, in a sense. Otherwise, you go to the full global static analysis.
But you could find necessary condition on the runtime type.
Yes.
You do that?
No. We could also merge and reason in terms of subtyping, for example, because we could merge some specialization under subtyping.
Last question while our last speaker sets up.
Do you have any experiments on other code bases in Hack for this?
Not so many. We in Java, for example, we were a bit less successful. I first tried to resolve virtual calls with Java, but it was Android code base. And here I suspect that we don't have enough context in a sense because we don't understand the life cycle of object. We don't have enough context.
Thanks, David. All right, thanks again, David. And last but not least for this session, Christian is going to talk to us about history repeating itself.
Okay. Hello, so my name is Christian and I'm going to talk about some ongoing work we have on distributed algorithm verification and how cyclic message histories are a useful abstraction for moving towards more automated verification in this area. And so to start out with, I want to start off with the problem statement of what are we actually looking at in this space. And so for the purpose of this talk, we're focused on safety properties, where we're interested in taking distributed systems and showing that an unsafe state is either unreachable or may be reachable. And like in most contexts, figuring out how we get to an unsafe state depends not just on the unsafe state itself, but some sort of execution history from some presumably safe initial state. But what makes distributed systems a bit more complex in this space is that rather than dealing with just one program state, we're interested in a bunch of processes shown here as circles, and the interaction of these processes can lead to something unsafe. And so on top of this, we also need to consider how these algorithms are designed in the first place. We're not interested in designing an algorithm that works with 7 processes and then redesigning it when we need 10 and then redesigning it further and further. These are all designed to be configurable. And so for the rest of this talk, I'm going to use this one-shot leader election example where essentially every process is going to start out, set a vote counter to 0, set a leader field to -1, pick a process it's going to vote for, send that info to every process, And then whenever a process gets a vote for itself, it's going to increment that vote field. When it gets more than half the votes, declaring itself a leader. And whenever you receive a leader field, whenever you receive a leader message, set the field accordingly. And if you've set it more than once to a different value, throw an error. And so, importantly, this algorithm doesn't depend on any specific system size. We want this to be general for whatever sort of deployment we're interested in. And so with that in mind, what does an execution history actually look like in these systems? We're going to look at this sort of message passing or event-driven model where each process is going to send and receive messages, and whenever they receive these messages, they're going to react by executing some block of code. And in this case, our execution history is not just the state of the program itself, but a history of which messages have actually been received in which order, which allows us to start from some initial state and essentially read off this history to reach the current state. And so the history for a particular process might be that you receive an initial message, you receive 2 votes messages, and then you receive a leader declaration. And these histories depend on the configuration. If we have a system of only 3 processes, you might see 2 votes before you see a leader declaration. When you have 5 processes, you might see 3 votes and then the leader declaration. And in general, as you get more and more processes, this history is going to grow. But it's not just growing at random. Our history is changing predictably. In particular, no matter what our configuration is, we're going to start, a process is going to get some initial message. It will receive at least 1 vote and potentially some unknown number of additional votes before it can actually receive a leader message at all. And so with that observation in mind, in this work, we define a mechanism for over-approximating these sort of cycles in distributed algorithms. And in particular, we're going to talk about how you can use goal-directed analyses with abstract message histories in order to efficiently explore the state space of these programs. We're going to show how handling cycles boils down to parametrizing these abstract histories on the configuration, and how, analogously to parameterizing the history, we can parameterize the processes themselves and end up with these sort of summary processes. And so, at a high level to start out, our analysis is going to start off in some unsafe goal state. It's going to step backwards, and as it does so, it's going to build up some sort of message history and potentially add new processes that are relevant to our goal state. If it finds a cycle, it's going to attempt to summarize the messages and processes involved in the cycle. And it's going to continue this process until, ideally, we either find a contradiction or we find an initial state and know that there might be some error. And so the first piece of all of this is a goal-directed analysis. So we're going to start in an unsafe state and attempt to refute reachability, where in our case, the unsafe state is that you get leader messages for 2 different leaders. And so we're going to start off in some unsafe state and attempt to step backwards into what was presumably safe at some point. And so our goal state is the unsafe state. And we're going to leverage separation logic here, where our goal state doesn't contain every process in the system, only the ones that might be involved in the error. And so at our beginning, it might be one process that has received a leader message and has just received another leader message. We're going to build up backwards from this point and add processes as needed as they become relevant to the goal. And we're also going to build up a message history. And I'd like to point out here that this message history looks a bit different than our previous ones. In particular, when moving from a concrete message history to an abstract history, because we're only looking at some slice of the system, rather than this encoding the entire history in between each message, you can have essentially an unlimited number of other messages as long as they don't affect this sort of like relevant slice of the system. And so we're going to start off with our one process and an empty history of, well, we don't know what the past looks like currently. And with our algorithm, the first thing we need is that, okay, well, a leader message had to happen at all. And so we're going to move to a state where, okay, some process sent that leader message, and so we're going to have that process as well, and a leader message in our history. For a leader to have occurred, someone needed to vote for that process. And so we're going to extend our history accordingly. And again, there might have been another vote. The process may have received more than one vote. Recall that every time a process gets a vote for itself, it's incrementing some sort of field. And each time we step back, we're sort of decrementing from some unknown value of votes. And so we can do that again. And we could choose to do this again and again. And what's important here is that we need to witness this sort of vote an unbounded number of times where if we had an exact configuration of processes, we'd know exactly how many times we need to see votes. But we don't have a fixed configuration, so how many times is enough to see this vote? Whenever a process gets more than half of the votes, then we're done. But what is half? Half of what? And so with that, we're going to talk about how we can parameterize these histories on configuration. So approximating cycles isn't a new idea. It's been done in sequential programming forever, where we have some loop and we want to find a loop invariant. And intuitively, we want to try and think of these cycles as being loops. And we have a loop, we want to find some sort of invariant for that loop. And in particular, what we know is that we're going to receive a vote some number of times we'll call phi. And based on our algorithm, we know phi has to be at least, or has to be greater than half of the processes. And so we have this special message here that's parameterized on our configuration and a constraint over the actual value. And with this, we step back, we witness some unknown number of votes, and then we can continue our analysis. We've seen vote as many times as we need. But there's one more piece to this, which is what about all of the processes that are actually voting? And so whenever we're stepping back, as I mentioned before, we're going to add processes to our system slice. Every time we see a vote, something needs to have sent that vote. And so if I had a fixed configuration, say there were 5 processes, I could add 3 processes to my system and step back. But we need 5 processes. How do I add 5 things into my goal state? And the thing to note here is while we need to add 5 processes, each process is going to have the same constraint initially that they need to send a message, they need to vote for the same thing. And interestingly, while they start with the same constraint, they might take different paths to reach that send, and so constraints on each process going backwards might not stay the same. And so it's not enough to just say, okay, well, all of these processes are replaced by one process. But what we can say is that while different processes might take different paths, some of them might take the same path. If I have 10,000 processes, probably some of those are going to take the same path. And if we have some set of processes that take the same path, all of the constraints over them will look exactly the same. And so rather than keeping each of these as a separate object, we can summarize them into a special process here shown PK, where PK stands in for P1, P2, and P3, and potentially some unbounded number of these processes. And when concretizing, PK will become some set of processes. And so with that, we're going to start with our unsafe process. It sees a leader message, it steps back, it sees a previous leader message, it sees a vote. Instead of seeing vote again, we recognize that if we do this, we will end up in a cycle. So we summarize that voting process, and we summarize our message history, and then we continue to step back with the cycle resolved. And so all of this sounds nice in theory. What have we actually been able to do with this so far? So currently, we've built up a tool for analyzing P programs, where P is a modeling language for message passing systems. We're able to prove this one-shot election example safe without explicitly picking a set configuration like you would with a model checker. We also expect that this approach will apply to other consensus algorithms, where they have this similar sort of structure of initializing, sending some number of votes, reaching a quorum, and then proceeding, where reaching the quorum is the sort of vote cycle we saw in our first example. So we expect that this will apply to this sort of class of algorithms. But there's still some limitations, and there's some future work to explore in moving in this direction, where if we have a bound number of unique paths, then each of these we have some finite number of summary processes. But what if there's an unbounded number of these? And this can be looked at with some sort of reachability analysis. How do we get the best constraint possible on phi? How can we leverage other information we might have about the system, like its topology? What if it's a ring? And how do we know that this scales with the message history? As the system gets bigger, how can we deal with reordering some messages that might not matter for our goal? So that's all.
I have not understood how you get your phi. I have a suggestion. When you have a loop, you add a counter, then you make a relational analysis. It's relate variable to the counter. You eliminate the counter, you get it. You have a similar technique or no?
Yes, in the implementation, we're currently leveraging a recurrence analysis to sort of solve out for a closed form solution of what phi needs to look like. And that's also where we get the constraint over phi, where it comes from in our algorithm. Every process votes once. And so this is sort of where the reachability analysis in the future work comes into play, of ensuring that there's this interplay between the reachability and the recurrence analysis to get the strongest constraint we can find.
All right, earn your coffee break with one last question. No? An unearned coffee break? All right, well, thanks again, Christian.
Okay, great. So yeah, originally the title was Reduction and Completeness, but I received some feedback during review, and I decided to have a more relaxed talk, and I'm sure everyone's brain has already been fried from the 20 different incorrectness logic we have seen today. And so I didn't add a lot of math in there, but I would give an overview of how to work with clean algebra and how does it connect to program logic and what are the future works that we can do in this respect. And the topic and the title is when algebra marries program logic. It's slightly inaccurate. It's when algebra proposes to program logic, because there's still plenty of work to do, and I believe there's a promising aspect of this. And so let's recap on the core semantics of program logic, which you have already seen 20 times. You start with some precondition, you execute some program on this, and you reach some ending values. And in this talk, I will call them codomain, and some people call them range of the function. It's the same thing. And then you compare the codomain of the function with some postcondition. If the codomain is contained within the postcondition, then we got Hoare triples. And if the codomain contains the postcondition, then we got incorrectness triples. And so you see, like the building block of a program logic, you have program and you have predicates, and then you need to compare codomains, right? And this is where TopCat came in. And TopCat consists of 3 different components. It contains top, ka, and te, right? So ka is ka, and te is test, right? So for clean algebra, it's an algebraic system for regular expressions. So it gives you a lot of the desirable structures that you need to program. For example, branching, sequencing, and iteration. But in regular expression, branching and iteration are non-deterministic. That is, you cannot guard them by a condition. And that is where tests come in. So tests are intuitively predicates on memories. And they are basically conditions that guards the program intuitively. And with that, you can get conditional branching and conditional iteration, which corresponds to if statement and while loops. And besides that, because tests are predicates on memories, they can also serve as predicate within like the program logic. Right? If we look at clean algebra with tests, they already have most of the things that program logic needs. So we can think of clean algebra with tests as an imperative language with some extra features. For example, it can also express predicates, and it has non-determinism. And in fact, with clean algebra with tests, it's already enough to encode Hoare logic. And this is a very early result by Cozen. And so another nice thing about cat is that we can put cat pictures on our slides. And this started a lot of cat meme within the community. And in that vein, TopCat is basically a fancier cat. And no, that's not true. Unfortunately, as a computer scientist, I sometimes do need to do computer science instead of posting cat picture all the time. So top are for codomain comparison, which is the last step we need to model program logic. And notice in this talk, we will only talk about codomains, but for domains, it's the same. For domain, you are basically doing like the backward reasoning that people have talked about. And the system can also be extended. It doesn't need to be extended. It can also model like domain comparisons. But we only show codomain as examples. So here are 2 simple programs, right? So you only have 2 memories. Program P sends both memory into memory 2, and program Q doesn't change the input memory. And we cannot directly compare them, even though program P has a smaller codomain than program Q, right? We need something to help us extract the codomain. And this is where top comes in. So in here, I imagine top as a complete relation. I define top as a complete relation. And when you compose a complete relation with another relation, it kind of normalizes the domain and the internal transition within the relation. And in the end, you can compare the codomain once you pre-compose with top. And if you post-compose with top, you get the comparison between domains. And if we look at the semantics of program logic, they're basically domain comparisons, right? And the Hoare logic says if you guard by P and then execute guard by B, then execute P, its domain should be smaller than the domain of C. And that's exactly the encoding of Hoare logic, which is top BP, which is extracts the domain codomain of BP, and top C, which extracts the codomain of C. And similarly for incorrectness logic, you just need to switch the inequality. And this encoding turns out to be surprisingly successful, because we were able to derive all the proof rules of incorrectness logic and Hoare logic just with this encoding. And by proof rule, I mean like structural proof rules, which exclude assignment rule, because in here we don't have definition of assignment. And this is a very nice story for Topcat, right? I talked about this on POPL 2022, but actually I was a bit hesitant. Because our intuition are fully based on relational model, and it's a very restrictive form of relational model, right? The top elements are required to be the full element, which is like the complete relation. But why does the algebra able to encode like these two very powerful logics, right? These two logics are relatively complete, which basically means like they can derive anything with respect to relations. And indeed, we have a way to characterize how powerful a certain algebra is. It's called completeness. So for an algebra to be complete with respect to its relational model, it says all the inequality that holds in every relational interpretation can be derived from the algebra. In other words, the algebra is powerful enough to prove all the inequality that holds in every relational interpretation. If this holds, then it gives us an explanation of why Topcat is so powerful, even though our intuition is based on like a very restrictive type of model. And typically, how do we prove completeness in linear algebra, in the like extensions of linear algebra? We start with a theory, and we develop a complete interpretation for that theory. And this is typically the hardest part of doing the completeness proof, and we will see later. And then we embed the complete interpretation into relational interpretation. Basically, going from a complete interpretation, we construct certain relations that preserves all the equalities within the complete interpretation. And for linear algebra, the complete interpretation is a regular language. So it basically computes a regular language from the regular expression. And this is only proven in the 1990s, which is way after when regular expression was introduced. So as you can see, it's a very hard proof. And then we can embed regular languages into some relations. And this actually predates the completeness of linear algebra. This is proven in 1970s. So you can see like the first part is really the hard part. However, for linear algebra with test, its complete relation or its complete interpretation are program traces. That means two programs are trace equivalent if and only if they can be their equivalence can be proven by the theory of cat. And this it's proven, I think, in the early 2000s. Why is it this fast, whereas the completeness of linear algebra took like 20 years? It's because they use something called a reduction technique. So instead of proving everything from scratch, it basically reduces the completeness of program trace into the completeness of regular languages. And in this way, people don't need to prove completeness of program trace from scratch. They can leverage the completeness of regular languages to prove the completeness of CAT. So however, in this case, we need a reduction both from CAT terms into clean algebra terms and a reduction from program traces into regular languages. That's like the previous proof that most people, most literature follows. And then we can embed the program trace into input-output relation. That is very easy. And we want to do the same thing with TopCat, right? Because we have this very powerful algebraic system, and we don't know why. Because, maybe it's complete with respect to relational model. Then it explains why it can model the entirety of proof rules of incorrectness logic and Hoare logic. And we were able to streamline the reduction so much that the reduction no longer needs to mention the semantics. We can directly do the reduction on the algebra. And this is a very nice proof using properties of universal algebra, which is what I used to want to focus on, but now it's this. It's fine. And the complete interpretation of TopCat is program traces with top, which is like the full element, and sometimes are called havoc. So it's the element with every single trace possible. So this element can execute anything. And the completeness becomes a corollary of the reduction in here. So we can push the reduction down each step. And turns out if we want to push the reduction down for relational models, everything blow up. Right? Indeed, relational model turns out to be incomplete with TopCat. And this is inequality that we discovered in 2022. This inequality is true for every single relational model, but it's unprovable using the theory of TopCat. And later, Damien Po and Jana Wagemaker in 2023 proved that if you add this as an axiom, then TopCat is indeed complete with respect to relational model. But I was not satisfied, because look at this picture. When we were able to derive the incorrectness logic and Hoare logic proof rules, we don't need that additional rule. And why is that? Indeed, I think we later discovered that if we are doing things with all inequalities that holds in every relational interpretation, it's an overkill, right? We are only using the top element to extract domain and codomains. So we later showed that if we restrict the inequalities that we are looking at with codomain and domain comparison inequalities, which are like pre-composition with top or post-composition with top, then we can actually prove the completeness by using the language interpretation or the complete interpretation. And finally, we can say, always has been. Okay. So yes, so it's all algebra at this point, and we have proven that TopCat is powerful enough to encode both incorrectness logic and Hoare logic, and we have shown why it's so powerful, and using like the theory of TopCat. And then why is TopCat useful? Why are we interested in this? And I will give some perspective on what future work and how do I envision TopCat is going to be used. But first notice that this is a question you never want to ask because you will upset a little cat with a top hat. Look at how sad that little guy is. Seriously, why would you doubt his usefulness? So for now, I think a good use of TopCat is a semantic foundation. So if in your semantic domain, you find that there's a top element, then you automatically get incorrectness logic and Hoare logic out of it. So I think that's kind of nice, and it's a very fast thing to check. Unfortunately, a lot of the interesting domain doesn't satisfy this property. For example, probability. There's no largest probability, right? The probability are always sums to 1, and if you compare two probabilities, there's no one that is there's no largest probability distribution. Yeah, okay, and I also want to encode more program logic features like relational reasoning, which has already been done, but we recently proved that their system is undecidable. And this will be a talk in Netherlands by Arthur de Amorim. If you are there, it's very good. And I also want to encode notions of separation and abstract interpretation and symbolic executions. And for separation in particular, I think it might help us to speed up tools developed around clean algebra. And finally, as an automation tool, I don't know why the tool looks like this. It's supposed to be pretty big. So as an automation tool, so I was hoping, like, because clean algebra are famous for being decidable and usually very fast, so can we automate some of the decision procedure of program logic using algorithms within clean algebra and clean algebra's test? And finally, it gives us more chance to put cat memes in our slides. Okay, great. Yeah, please. Yeah. Thanks. Oh yeah, right. So I think that's a very good thing to explore, because like the reachability property can be expressed using top in a very natural way. But yeah, we just didn't have time to do that.
I was asking to myself, is a cat ad hoc or not? So to answer this, I ask you a question.
Yeah.
If I change all logic to Mueller-Mana logic, which is all logic with for total correctness.
Oh yeah.
What happens?
Oh yeah. So this is a very hard thing because in cat, as far as I know, there's no notion of termination, but in a recently developed system called GCAT, I think we can do something there because GCAT has a notion of non-termination, early and late terminations, because it's more closer to a process calculus. It's in between process calculus and clean algebra. So yeah, so I think there might be something there, and it's very interesting, I think.
But it's not the cat.
But it's not something cat can do.
So it was ad hoc.
Yeah, it is. Yeah.
Yeah. Can you elaborate more on introducing abstract interpretation in this business?
Oh yeah, right. So
you mean that you want a lot an algebra for expressing the fact that two programs have the same abstraction, or something like this?
Yeah, right. So abstract interpretation is a lattice-based system, right? Well, I'm nervous now.
Already the top is an abstract.
Yeah, and it's very order theoretic, and and cat itself has a very nice order theory surrounding it. So I was wondering if there are some connections, and if we can use abstract interpretation to abstract TopCat, or can we use TopCat to abstract interpretation in a sense like that? Okay. Yeah. Great.
Thanks again.
Thanks.
Right. Our next talk is by Yongwei on From Traces to Incorrectness. So whenever you're ready and mic'd up, please take it away.
You have to guess which one you are here.
Ah.
No, it's a different color.
Oh, yeah. Sorry, it's so small. I should have made it bigger. Well, anyway, my name is Yongwei, and today I want to present From Traces to Incorrectness, type theoretic approach. This is still ongoing, and actually we will talk about some past work and then pave our way to the current work. By the way, this is joint work with my colleagues from Purdue University, Jojo, Julia Belkova, Benjamin Delaware, and Suresh Jagannathan. So, right, we've already seen a lot of incorrectness logic. We know that incorrectness logic typically concerns reasoning of imperative programs. But when we shift our focus to functional programs, it poses the question that, well, what does an incorrectness type look like? To answer this question, well, the straightforward way will be try to incorporate the incorrectness triple like a type, right? And then the middle bit in the triple is a refinement type that captures the reachable values of the expressions. But the problem is that, well, types is good because it brings a lot of compositionality in the reasoning. But when we look at these two triples derived from these two subterms, E1 and E2 in the program, the question is, how can we compose them? So to answer this question, let's first look at, well, this is look at a abstract program where the green dots represent program states and the blue circles captures an incorrectness triple, which under-approximate the program behavior. Imagine that the program state here are captured by traces, like, okay, as in sequences of past events the program has already produced. And then the transitions here, we can think of them as transducer over those traces, because when we transducers are essentially a function that takes trace and returns trace. And because of that, we can think of transducers as a state transformer, where the state are represented by traces. I will elaborate what those traces are and how they can represent the program. But the high-level idea is that we want to incorporate this transducer idea as part of the type system to reason about the incorrectness. But before then, I need to talk about some background, which is first, type usually represent over-approximate behavior of the programs, right? So we first need to talk about, okay, what does under-approximate type means? We will first talk about this work, coverage type, and then I promised that I need to discuss what those traces represent and how they can capture the program effects. This will be the work Horde automata type. And at the end, we will see how we can combine them, and also the transducer, which hopefully the resulting type system will allow us to do incorrectness reasoning for functional and effectful programs. Right. First, coverage type. So why coverage type, or what is coverage type? Here is a little natural number generator. What it does is simply it first generates integer x, and then if the x is non-negative, we just return x. Otherwise, we return 1. So, and here, and on the right-hand side, we have two types. One is the standard refinement type. The other is a coverage type. It's obvious that if you're familiar with refinement type, it's obvious that the natural number generator here always can be assigned this refinement type because it always generates, the value it generates is always non-negative. But on the other hand, this coverage type cannot be assigned to this program because what, right? This is what I want to answer shortly. To answer that, like we need to understand what are refinement, what are coverage type, especially in contrast to refinement type. So notice that they have similar structure. they both have a self-reference to the value v. They both have a base type, and also they both have a qualifier that talk about that qualify the value v. But their semantics or their meaning are very different. Refinement type typically talks about the safety of the program. It says, well, for all value v that the program can reduce to, it should satisfy the phi. So the qualifier captures the safety of the program. On the other hand, coverage type concerns the completeness of the program, in the sense that, notice that we swapped the conclusion and the condition in the formula such that it essentially says, well, if a value satisfy our qualifier v, as in here it says, if for all non-negative values, the expression should be able to produce it. Well, this is, and then with this completeness mental model in mind, we can go back to our program. This natural generator is a natural number generator is not complete with respect to the coverage type specification because it cannot produce 0. The fix is simple. We just replace the 0. We replace the second branch 1 with 0, and then the natural number generator can indeed produce all the natural numbers, and the coverage type check succeed. So, so this coverage type, why would we need to talk about this coverage type? It is a form of under-proximal reasoning that concerns purely functional programs. But like the incorrectness often concerns effects, and let's talk about how can we use program traces to capture those effects. Here is a simple functional client that talks with effectful libraries. And the effectful libraries is here. The effectful library is an integer cell, has 2 API calls, read and write. How can we reason about this program? Well, we can augment the small step operational semantics that works on pure programs. We augment the operational semantics with traces, where we first have where the reduction of the term e begins with a context trace that captures what has happened before. It also, and then the second part, and then we also keep track of, okay, what are the new event produced as we reduce e to e prime. To ground the discussion, let's look at what those traces are. Let's say we evaluate our little program starting from a trace where there was a write 3. So, and then we know that the read will return 3. And this reading event will be tracked as we evaluate the program to write 3 plus 1. To further evaluate this program, we append the new event read returns 3 to the existing trace, and then the write 3 plus 1 will produce an event write 4. So with this kind of with this operational semantics that operate over traces, we can use it to captures Hoare-style reasoning where we have precondition and postcondition. Let's say for all the traces in the precondition, if we evaluate our term e under this trace and produce beta, then the context trace alpha concatenated with the effect trace beta, it should satisfy our postcondition. So really, the precondition and the postcondition are represented by a set of traces, which more concretely we can use regular expressions to represent them. And this whole automata type essentially says, well, if we evaluate this program, given that a non-negative integer was written, then the program, after the program evaluation, we ensure that the last event is also a write with non-negative integer. So I promised that we need to talk about incorrectness, but a more straightforward way will be just talk about how we can refute this whole automata type. And the refutation of whole automata type can be written like this, which is trying to find a preconditioned trace alpha and find an execution that produce some effect beta such that alpha calculated with beta is not satisfied by the post condition B. Like we're not diving into this in this talk, but we have tried to use symbolic execution and the derivative of regular expressions to guide the falsification problem here. Please feel free to you're recommended to go to tomorrow's talk at 11. So here what we are really interested in is how we can then plug in this transducer along with those under proximate reasoning idea. As we said at the very beginning, transducer will allow us to allow compositional reasoning of the program. Well, what are the transducers? For example, the behavior of read here can be captured by a transducer that takes the input trace write x, and it simply directly returns this output trace. On the other hand, the write operation here its behavior can be captured by another transducer that takes in write x as the input trace and returns write x plus 1 as the output trace. And so the transducer here we're talking about are really symbolic finite transducers, and which means that because there are many other possible pairs of traces that captures the behavior of read and write. And by leveraging the published result on symbolic finite transducer, we can easily compose these two transducer, which essentially compose the behavior of the subterms. What the composition does is essentially taking the output trace of the first transducer and match it with the input trace from the second transducer. Right. With that, let's plug the transducer to a type. Here we have an under proximate type from before, from coverage type, and it's attached with a transducer T. So here, the denotation of this type essentially says, well, for all input-output pairs of traces in the transducer, the program is able to witness them. And interestingly, this transducer, the denotation of this transducer is analogous to what the incorrectness logic does if we consider a weaker version of the formula. So the range or the codomain of the transducer essentially represents the reachable post state of our program, while the domain of our transducer, the input traces, acceptable input traces to this transducer captures the presumption of our program. And then the formula essentially says, well, for all reachable post state, there exists some pre-trace that will allow you to find an execution of the program. that lead to the post state. With that, I want to quickly summarize here that the transducing type is for incorrectness reasoning, a functional program that interacts with effectful libraries. We use under-approximate refinement type to capture the reachable values, and we use the transducer as a form of forward state transformer. Yeah, with that, I'm happy to take any questions.
So I was wondering, how do you compute the transducer for like read or write? Because that do user need to annotate those, or?
Yeah, for now our idea is that we ask user to provide them.
Essentially, I had the same question because in the refinement type, the phi must be finite.
Phi
in the refinement, you see you have finitely many phi. And I was wondering, what are you doing if you have infinitely many, but you also assume you have finitely many phi here?
Phi is qualifier.
Yeah, this is a property. So in terms of abstract domain, you have finite abstract domain.
Yeah. Here we mostly consider like discharge those qualifiers to SMT solver. So we haven't really looked at abstract domain and things like that. Yeah.
You have, but they are implicit.
Implicitly.
Let's thank the speaker again.
Oh.
The mic.
Sorry.
Okay. Our next talk is by Naifeng on semantic lifting for scientific computing. Please.
Thanks for the introduction. I'm Naifeng Zhang. I'm currently a fourth-year PhD student at Carnegie Mellon University, advised by Professor Franz Branchetti. And today I'm going to present our work on semantics lifting for scientific computing with a case study on FFT. So after I learned all these very excellent static analysis techniques, hope our approach will bring a different flavor to the table. So first of all, we define the semantics lifting as deriving the high-level semantics from the source code and usually written as a mathematical specification. And why do we care about code lifting? So I think there are two major reasons. The first one is we can answer the question that does the code achieve the desired functionality? And this is particularly useful if the code is not written by the user, but for example, generated by a large language model, which is pretty common nowadays. How does the user know if the generated code actually does what it's supposed to do? And the second reason is that code lifting gives us a portability where we can lift source code to a high-level specification. And then from that specification, we can go to other programming languages. So for example, if we lift a Python code, which is not very performance-oriented, to a high-level specification, and then use a code generator to generate a C or CUDA code that could possibly give you a performance gain. So currently, there is a very active research area called verified lifting. So they use SMT solver-based approach to analyze the looping variants, preconditions, postconditions. But in the domain that we care about, which is scientific computing, using the verified lifting seems a little bit challenging. So this is because in all these scientific kernels, it involves real and complex numbers. It involves transcendental functions, such as sine, cosine. And usually, the kernel is implemented recursively. So to just give a very concrete example, if we ask GPT-4 to provide a C implementation of the fast Fourier transform, FFT, so if you're not very familiar with FFT, just remember it as a very core and fundamental scientific kernel. And I will give more context on this in a later slide. So this is the piece of C code that GPT gives us. Then our research question boils down to, for this very specific example, That is, does this piece of code implement the fast Fourier transform? And as you can see from the code, it involves complex numbers. It involves, it's implemented recursively, and it involves functions such as sine and cosine. So in our first try, we found that we can actually kind of solve this using symbolic execution. So for a fixed small input size. So for the input size, I meant the, oh, can you see my mouse? I meant the int n here on the line 4, which defines the dimension of the FFT kernel. And because FFT is a linear transform, it can be represented as a transformation matrix where you act on the input vector, and then you get the output vector y. That's your output. And for example, if we set n to 4, a very specific size, we can actually use symbolic execution to act on this piece of code and give us this transformation matrix. And using this matrix, we can do equivalence checking with the knowledge base we have and say that, oh, indeed, this piece of code implements FFT, but just for n equals 4. We can do this for n equals 4, n equals 8, n equals 16. But then the runtime for symbolic execution just grows very rapidly. And as you can see from this piece of code, it kind of like works for an arbitrarily large n. So what do we do from here? And this is what we propose. So this is a very, very preliminary work. And our experimental approach is stepwise semantics lifting. So we first make 2 assumptions to constrain the problem that we're trying to solve. The first assumption is that the source code implements a linear transform. And actually, this spans quite a wide range of all these scientific computing kernels. And the second assumption that we make is there exists an expected mathematical specification of the source code. So for example, if the user prompts a large language model, the user knows what he or she wants. And right now, we have these 2 concepts. We have source code. We have a mathematical specification. It's kind of hard to compare them. So what we propose is we step by step lift it up to one intermediate representation and then to another intermediate representation to as far as possible. And hopefully, we can arrive at another mathematical specification. And now it's much easier to compare 2 mathematical specifications. So let's take a look at this, this left part. So if we start with a very high-level mathematical specification, we lower it into one IR and to another IR and eventually to the source code. This is commonly known as the code generation. So this is why we try to investigate our proposed approach using a well-established code generator that is called Spiral. So what is Spiral? Spiral is this code generator that's specifically, so initially designed for linear transforms, but now we're expanding this to an increasing list of mathematical functions. So it has been developed for over 25 years. And in Spiral, we have 3 intermediate representations. So the first one is a formula-based IR. It's called a signal processing language, SPL. So SPL captures the mathematical semantics of the kernels. It also captures the functional data flow of the target algorithm. And the second IR is a loop-based IR. It's called Sigma SPL. This captures all the loop abstractions. And the final IR, it's I-code, which is an abstract internal code representation. So over the past 25 years, we start with a high-level mathematical specification in Spiral. And Spiral lowers it down to SPL, Sigma SPL, applying optimizations along the way, then to I-code. And from this I-code, we can then target different platforms, CPU, GPU, and even some specialized hardware. So what we are proposing here is to reverse this process that's been developed for 25 years to investigate if we can do semantics lifting. So today, I'm going to present a very specific case study on fast Fourier transform. So what is FFT? First, the DFT, the discrete Fourier transform, is a fundamental tool in science and engineering. And FFT is essentially a class of algorithms that reduces the time complexity of computing DFT from O(n) squared to O(n) log n. And for example, here I show a very well-known FFT algorithm called Cooley-Tukey FFT algorithm. And this is written in SPL, which is the intermediate representation that exists in Spiral. And it make use of identity matrix, make use of the Kronecker product. And this is the mathematical specification that we want to lift to. So of course, the Spiral also has this knowledge base of many other FFT algorithms. So now, how do we do semantics lifting? So we start with this same piece of code I've shown before in C. And we first use a claim to dump the abstract syntax tree. And then we walk the abstract syntax tree to transform this C code into I code, which is the last layer of the intermediate representation in Spiral. So now we can put the source code into a domain that Spiral understands. And in this presentation, for the sake of time, I will specifically focus on the first for loop. And so as you can see, it's a line 17 to 22 here. So this is I-code, the internal code abstraction in Spiral. And what we do now is we analyze the indexing pattern of all the variables, the input and output variables, and the loop bounds. And then we can derive this mathematical formula, and which is sigma SPL. So essentially, a E here is a sigma SPL object that stands for a basis vector. So it has a 1 in one of its position and all 0 otherwise. So in this example, the E here is a 1/2n vector with a 1 in the 4j plus I position. And what we're doing here is this is essentially the access pattern if you treat all the inputs as a vector of 2n. So by multiplying these together, you're accessing the 4j plus I position. And we also have another E to capture the writing pattern, like how we write to the output variables. And essentially, that's how we use the mathematics to capture the for loop here. And then we do pattern matching to lift sigma SPL to SPL because this kind of scary mathematical formula can actually be nicely captured as an SPL object that is a LN2 bar. So LN2 bar is a stride 2 permutation for a vector of n complex numbers. And the bar here means the data type is complex. And essentially, we apply what we did in the last slide to all the section of the C code that we have. So we have the blue section, that's what we just shown in the last slide, which corresponds to the LN2 here. And then we have the other for loop, that's the green section, that's get lifted using the same strategy to the green part here. And then for the recursion in this piece of code, we capture this as we treat this entire code, because it's a linear transform, we can treat it as a matrix. So we let it to be an n by n matrix, that is the mn here. And then the recursion is captured as the mn over 2 matrix. So essentially, we apply what we had in the last slide to all the code sections in the source code, and we can derive at this mathematical formula. So now, what we go from there? We still don't know if mn is FFT or not. So remember, we talked about we can do symbolic execution on small sizes. So we can actually set n to 4 to 8 and perform symbolic execution to derive these two equations here. And these can serve as the base case. And because we already have another equation that defines mn based on mn over 2, we can perform induction. So by induction, we know the base case is DFT4, DFT8. That's defined on DFT2 and DFT4 respectively. We can then use this as the induction step to derive, oh, indeed, this piece of code implements DFTN. And now, since we have one mathematical specification, we can do equivalence checking with this vast knowledge space that Spiral has within its code generation system. And we found out, oh, this is indeed one special case of the Cooley-2-key FFT algorithm. So, yay. And there is a lots of future work since this is currently a very early idea, and we're basically presenting a roadmap of how we plan to do the semantics lifting. So we acknowledge that the problem of deriving the formal semantics of any piece of numerical code in general may just will be unsolvable. But for the class of algorithms that the spiral system understands pretty well, the problem now becomes more tractable. And this specific class of algorithm that Spiral understands is a well-defined part of a floating point computational science and engineering algorithm. So it works very well for our domain, that is scientific computing. So what we're doing right now is we're trying to evaluate the proposed approach on a wider range of algorithms. We already tested on different pieces of the FFT code, and we're also trying to work on matrix vector multiplication, matrix multiplication, convolutions, etc. And currently, as you can see, our approach is mostly about how to use linear algebra manipulation to lift the code semantics. And we can actually improve this guarantee to a formal guarantee where we're looking at integrate with SMT solver to formally prove the correctness of each lifting step. So thank you very much. You can learn more about Spiral at spiral.net, and I'd be happy to take questions.
What you lift is the concrete program which is supposed to work on reals to a specification that work on reals, but the program work on floats, so it could give completely different result. In particular, the programmer could have made rounding, and then what is the real? You don't know.
Right.
So at the end, you seem to say, yeah, but in some cases, I have a guarantee that it will work. That's what I understood.
Right. So I think particular because of this floating point running arrows, we're not like trying to lift for specific inputs, right? We're trying to look at the entire linear algebra that's captured inside the code. So in that case, it's supposed to work for all kinds of the running. So it will. So in that case, the running arrow will not matter that much. I think that is what I'm trying to say, if I understand the question correctly.
Yeah, but so you seem to say if I have only linear expression, is no problem. That's not true. If you have loops, you can have a rounding error that makes the program diverge, where the real it would converge.
I see. So that we haven't really investigated as of now. Okay. Right. But that, right. But I think we can definitely incorporate like the error analysis in our approach to make sure to give another answer like, oh, well, this converge or type.
That's correct. That you could say if it doesn't work, it means there is a problem anyway in the program.
Exactly. So this is also what we meant by trying to lift as far as possible, because when we reach at some level where we found out maybe, oh, the error passes a threshold, we'll just stop there and say that, oh, we cannot give you a conclusion to be.
You should do the other way.
Like.
If your thing is good, the program must work and converge. That's more difficult.
So you're saying for code generation, like when we go down. So in that case, Spiral, I think, already have like error analysis built inside as the infrastructure. Yeah.
And they have guarantee that it will converge and so on?
They do have that. So they do have the infrastructure on that. But for lifting, we haven't put that into like lifting. So the lowering, yes, but for lifting, not yet. Yeah.
Our final talk of the day is by Yusuke from Kyoto University. Also, special thanks to Yusuke, who decided to still soldier on and give this talk, because as I understand, he was one of the victims of the leak and his room was flooded. So thank you so much for accommodating us still. Please take it away whenever you're ready.
Thank you for introduction. So hello everyone. I am Yusuke Matsushita from Kyoto University. So first, I would like to apologize to all of you about the flooding. Unfortunately, me and the co-author of this work, Ryo Wakiwataka, was in the same room, and like, yeah, Ryo accidentally made the trigger the sprinkler, and the flagging happened, and we are really sorry about that. But we thank from the bottom of heart all the warm-hearted people of POPL and the PL community, and also I really love POPL, so I'm really happy that the POPL and all the workshops are held just like this. So I really thank all the organizers of the POPL conference and workshops. So so anyway, this talk is super technical, so I don't have too much time. So I will be in haste. Yes. So today I will explain my joint work with Kengo Hirata and Ryo Wakizaka on concurrent quantum separation logic for fine-grained parallelism. So in this work, we propose concurrent quantum separation logic for modularly verifying quantum programs with fine-grained parallelism. Compared to existing quantum separation logics, our logic is the first to support concurrency and the sharing of quantum resources, and can verify various non-trivial quantum programs. And compared to, and below we illustrate an example of such a quantum programs. First, I start with a brief introduction to quantum computing. Well, quantum things may look fancy, but please take it easy. You need not understand them 100%. Honestly, even I don't. So the basic building block of quantum computing is a qubit or quantum bit. While a classical bit can only be either 0 or 1, a qubit can be an arbitrary superposition of them, which is technically a linear combination. For multiple qubits, we technically consider the tensor product, which accommodates exponentially many superposition of exponentially many classical qubits, classical bits. And please keep in mind the notation used for tensor product or composite state. And the gate applied to qubits are restricted to unitary matrices or especially linear maps. And for example, the Adamal gate gives a superposition by turning 0 to 0 plus 1 and 1 to 0 minus 1 with some coefficient. And also CX pronounced controlled X gate operates on multiple qubits. So it's a bit tricky. The result of any quantum computing can be obtained by measurement, which lets the quantum superposition converge to a classical state with a probability determined by the coefficients. Here is an example of a quantum program or a circuit. It applies the Adamal gate to X, followed by the X gate on Y controlled by X, and finally measures both qubits. Starting with 0, 0, after applying the two gates, we get a superposition of 0, 0 and 1, 1. And after measuring it, we probabilistically get either 0, 0 or 1, 1, which is stochastically dependent between X and Y. So this is a typical example of an interesting phenomenon called quantum entanglement. Mathematically, an entangled state cannot be simply expressed by the tensor product. Now we are ready to discuss the motivation of our work. Our work addresses parallelization of quantum programs. As is the case with quantum classical computing, it is a promising way to reduce execution costs. We illustrate in an example of parallelizing two circuits with a latter made atomic. And a clever scheduler can produce the efficient circuits shown on the right-hand side. But the scheduler is also free to execute the two sequentially in either order. As observed here, parallelization allows exponentially many execution traces. So we need a modular program logic for verifying parallelized quantum programs, which is non-trivial. Typically, the correctness of a parallel program is the uniqueness of the output. To achieve this goal, we propose concurrent quantum separation logic, which has the following notable features. First, our logic supports parallel execution of quantum processes. And second, it supports shared quantum variables, even when they are apparent right-right races. And third, our logic supports atomic expressions for non-interfered embedding of quantum circuits and parallelization. So from now on, I will explain our work in more detail. Our target language looks like this. It has primitives for quantum operations, and parallel execution and atomic block for concurrency, and classical heap operations and control flows. And here is an overview of our logic. First, as concurrent separation logic, the whole triple is equipped with an invariant, which is what is accessible at each atomic step. And the syntax of the assertions is shown on the right-hand side. And we have all the standard separation logic connectives, and also standard proof rules on them. And like the classical heap points to token, we introduce the quantum points to token, and which owns and asserts the state vector psi of qubit x. We can freely apply a quantum gate if we update the vector of the quantum points to token. Separation of points to token means not only disjoint ownership, but also disentangled qubit states. Also, we newly introduced a proposition called the qubit token. It asserts that the qubit x is alive or allocated, but its state vector is unknown. We have more interesting proof rules, which I will explain soon. In this talk, I will explain and demonstrate our logic with this simple running example. It applies non-commuting gates x and Adamar to y in parallel, which is apparently a right-right race. But still, technically, this is no real race condition. 0 controlled x and 1 controlled Adamar do commute thanks to the controls by the case where x is 0 or 1, respectively. Our goal for this example is to prove this core assertion, which gives the output of state vector precisely. The challenge in this example is that both processes can write to y simultaneously, because x can actually be a superposition of 0 and 1 in the quantum setting. So we need to distribute the write permission on y to both processes. How can we do that in a sound way? Our idea is to support a quantum version of a case analysis over the basis of a qubit. In this example, we split into two worlds where the vector of x is 0 or 1, respectively. In each simplified world, only one process writes to y. For example, if x is 0, then the one controlled Adamar gate does not change the state of y. This successfully eliminates the apparent right-right race and enables the standard separation logic reasoning. This idea can be formalized as the following rule for taking the This idea can be formalized as the following rule for taking the linear combination of Howard triples. It decomposes the target state vector in some basis psi and psi prime in the precondition, and then combine the outputs respecting the coefficients alpha and beta. Technically, we have the side condition that Q and I are precise or represent a unique or no resource. Now, using this rule, our goal boils down to the two sub-goals shown below. Now we can prove the sub-goals by resource sharing via invariance, a standard technique in concurrent separation logic. So here we show how the first sub-goal is proved, and the second one is proved in the same way. So we want to reduce this sub-goal to the two Hall assertions shown at the bottom. For that, we can simply move the points-to token of X into the invariant, which can be accessed by all processes at every atomic step. The proof rules for invariance are shown below. Now our proof is almost done. The whole assertion on the left-hand side can be proved easily. But how can we prove the whole assertion on the right-hand side? To prove such situations, we introduce the following novel proof rule for the qubit token. By this rule, we can get access to the points-to token for the qubit each atomic step. We call this the anti-frame rule by atomicity for the qubit token, because it technically adds a frame to the hypothesis instead of removing it as in the well-known frame rule. This rule allows atomic writes to the qubit that is temporary or restores the qubit state after the execution is finished, which does not interfere with other processes which can freely access the qubit. In our example, the one-controlled X gate does not update Y when X is 0, so we can use this rule to complete the whole proof. As a summary, we illustrate the complete proof of the whole assertion for this simple example. Of course, our logic can support much more complex examples, including one we showed when motivating parallelized quantum programs, and essentially we can use the same technique for the simple example. And interestingly, we can even verify parallelization of arbitrary commuting matrices. This is because mathematically, any commutative matrices are always simultaneously diagonalizable. We can use the linear combination rule for verifying this. So I was a bit in haste, but we finished this part. So finally, I will discuss our ongoing extension to probabilistic reasoning, which is interesting on its own. We want to support quantum measurements. And the primary challenge for that is to precisely reason about probabilistic behavior. And in quantum computing, the standard precise model for that is a density matrix, which is roughly a probabilistic distribution of state vectors modulo some equalities. Our idea is to refine the approach of demonic outcome logic, the work published in this POPL and lead authors by Noam Zilberstein, organizer of this TPSA. We are also based on a concurrent separation logic variant of that work. A key mechanism is a probabilistic combination of logic assertions. This solves the limitation of the existing quantum separation logic in particular. And for the model, we introduce a new mathematical structure called convex PCM, which is a hybrid of convex space and partial commutative monoid. And here is the teaser of our probabilistic quantum separation logic. So unlike demonic outcome logic, we introduce the concept of convex assertions with the convex Hall modality related to the idempotence of the probabilistic combination. Also, we manage return values as resources in separation logic, which is useful to model probabilistically varying return values. And for quantum things, we make the points to token assert a density matrix instead of a vector, following the probabilistic combination. And we can naturally support measurement. So finally, this is the conclusion of our talk. For future directions, we are interested in more powerful concurrency reasoning and also automated. Oh, what? Okay, so for future directions, we are interested in more powerful concurrency reasoning and automated optimization of quantum programs. So that's all. Thank you for listening. Thank you.
My intuition, which is vague, is that you proceed by kind of case analysis. But when you have loops, it goes unbounded number of cases. So can you show your loop rule, the rule for the loops?
So I haven't shown the. Okay. So thank you. Okay. So thank you for the question. So so basically, the case analysis rule is kind of the same thing as the disjunction rule in the usual whole triple. This like case analysis over the disjunction on the precondition, kind of. So like, and for while loop, so we can just use the usual reasoning rule. So if we target partial correctness, we can use invariant-based reasoning as usual. And if we target total correctness, we should use some other principle. But basically, it's just the same with classical computing.
And it is complete.
Actually, so I think we haven't precisely shown that, but so for non-concurrent fragment, I think the logic is complete.
Yeah, so the main crux of quantum is, of course, entanglement. So when entanglement is in play, do you have any inconsistencies with any of the Horde triple proofs?
So basically the answer is no. So we support any entanglement. So this is because our quantum points to token is multi-qubit. So yeah, this will explain. So the qubits for the quantum points token can be multi-qubit, and like after applying some gate like CX gate, we do have entangled state on this part. So we can like just support quantum entanglement. But so quantum entanglement is actually a very good question, especially for the anti-frame room by atomicity. So technically, we actually implicitly linearly decompose the background state so that X is not entangled with any other state. So I think this can be an interesting thing about entanglement.
Thank you. Let's thank Yusuke again.
Thank you.
So that's a wrap on TPSA. Thank you all for being here. You've made it after a day of fire alarms, unfortunate phone events, and floods. It's apocalyptic, isn't it? But thank you so much. So Noam, Jules, and I haven't decided yet if we will organize the third iteration of the workshop or not next year. But if you're keen, if you have ideas, stay in touch with us, let us know. And if there is demand, of course, we will organize a third one. It will be our pleasure. And as you know, it will be in Europe. It will be announced where exactly. But so let's have a round of applause for all of our speakers, our keynote speakers. Our student volunteers who made this all happen. All of you for being here and making this happen. Go on. And a special thanks to Noam, who, as usual, made it all happen behind the scenes. And Jules and I were more of just chipping in occasionally when there was some decision to make. But thank you, Noam. Okay. So go forth and analyze, and see you all next year.